is wave particle duality, or like, oh, it's a wave and then it becomes a particle when you choose to look at it. Like, I feel like the paradigm, but also the sort of the language that surrounds it has just done immense damage to people's understanding of the topic, both inside and outside of the field. And I would never describe things in this way.
Yeah, so to
Working on,
clarify, so you would
yeah,
adhere more to like a neo-Lorentzian relative.
yeah. In that I don't doubt the final outcome of a time dilation effect and a Lorentz contraction effect, but I'm interested in how they can be explained at a at the atomic scale with uh, direct electromagnetic forces and mechanical strain within the object itself as something, a direct process driven by forces that can actually be tracked rather than just sort of saying it happens,
Yeah, I think
which
the issue, right?
never
So
felt
so
very
like so
satisfying.
so check it. You have Lorentz, and he has in his postulation a stationary ether. We're moving
Hmm.
through it. And that
Hmm.
stationary ether is contracting the matter physically by a factor of like y.
Yeah, the
So then
gamma
it,
factor.
yeah,
Yep,
whatever it is, yeah. So then it's slowed down.
looks like a
It
line.
also
Yeah,
that same thing also slows down the
the
clocks by the
internal,
exact
yeah,
same
the
factor.
internal clock ticking. Yep, yeah, has to do both.
That's kind of crazy, right?
Yeah.
I mean, that's crazy. Like, why? Why would it do that? Why would it? Like, what physical
Well, I
reason does it
mean,
have to change them by the same exact factor?
because as complicated as all of matter may seem, there's only a couple forces that we know of that regulate the interactions between every proton and every electron, um, the electric force and the magnetic force. And it's like there's four Maxwell equations, each taken individually as a somewhat simple rule. Together, they lead to obviously matter with all the complexities that we see, which is kind of incredible. Um, but any physical structure is a bunch of charged particles being held by some bond of force at some stable distance from each other where forces balance. And any ticking process, any oscillation, any vibration of any kind is things vibrating because of forces that are driving them back and forth. And if at root level these forces scale by a factor that is, the gamma factor that is proportional to related to this thing that has to do with the velocity of an object, then that's going to proportionally scale every structure that those forces are responsible for creating. If the forces scale down in a certain way, then that's going to reduce down the frequency of any sort of ticking vibration between the pieces of something. And if the forces go up in a certain way, that's going to pull things closer together by that factor.
So basically, you're claiming that it would all change the same. Like, say that we had multiple different clocks, right? Like different types of measuring quote unquote
Yeah,
time. They would all change because it's based on ratio, like of the internal
yeah, because it's
components.
all, no matter how we try to make the clock, it's all the same fundamental forces. Like, unless we discovered a new force that worked in some radically different way, it's like it doesn't matter how intricate we try to make our clock or make our device, if at root level it's just one type of force that's holding the constituent pieces together, and that force scales up or down in a certain way, then that's just going to have a knock-on effect of what it's going to do to the entire object in proportion to the change
Yeah,
to the
but think
force.
about it. Think about like an atomic clock versus like a clock on your wall, right?
Yeah.
The the magnetic strength increasing in the atomic clock, the way that we're actually getting our time and the way that we're counting the clicks, basically the
Mhm.
oscillatory pattern, right, is fundamentally different than like say the size of this clock on the wall physically shrinking a little bit. And so, like, it
Sure.
doesn't have the same mechanism output that we call time. So, like, they wouldn't
What
in theory, if you get all the different types of clocks, then it wouldn't, like, give you the same with this if you all had the same velocity and the magnetic strength changed relative to that velocity in all of these different clocks, but they wouldn't give you the same time output because they have, like, a different mechanism of giving you the value.
Well, that's what I'm saying is that the mechanisms are based on the same types of forces when you dig down on it. It's like, okay, yeah, like with an atomic clock, it's very direct to see, why these, the particles, which are little sources of magnetic fields, why they're flipping back and forth at a certain rate. And if you reduce the strength of the magnetic field, that slows the rate they're flipping. And when you look at let's look at a mechanical clock, like look at like a watch, take one apart, and like this feels really abstractified away from the fundamental level of atomic electric physics, but like when you dig into it, no matter how complicated the gears are of a clock, what is driving it is the vibrations of a spring, of spring motion, um, of bits of metal that are flexing back and forth in a rhythmic way. So then you got to look inside the metal, and then you got to look at the flexing vibrations of the metallic spring down to the atomic level, and we're back to electric forces again. We're back to the exact same types of forces that are responsible for the ticking and flipping rate of the atomic clock. Like, you know, it's all the same stuff at the end of the day. It's all the same. What I'm trying to say is we would need to find something else, that is outside how the electromagnetic force works. We would need to find a new type of force in the universe that behaves in a different way for it to not be the case that all objects would just undergo the exact same amount of contraction and time dilation due to their motion.
Okay, yeah. I mean, I understand what you're saying. I think I disagree, but I think it's cool. I mean, I can look in my opinion, I have to look more into, like, each specific mechanism because it would basically be, like a cosmic coincidence that I know you're saying it's not and that it's overcomplicated because it all has the look, we definitely agree on that, right? Which is that it's like it's all fundamentally the same thing. It's all on the smallest scale, it's all fundamentally comprised of the same thing, but,
Yeah,
um,
charges.
yeah. I think the way
Now
that
we're
we relate that to what we call time is very nuanced with the actual measurements that we get. But well, just to remind you, this Clips is not full, right? It's like 96%. Does anyone know? I'm looking at this Eclipse, and it's still got a little bit of light. This Eclipse isn't a full eclipse, is it? Anyone know? It doesn't matter. Yeah, so, like, cause like, look, bro, my
It's a
understanding
it's a
what's
partial
up?
lunar eclipse. Yeah, it's a partial lunar eclipse tonight.
Yeah, it's like 96% or something?
Yeah.
Yeah. Okay, so then it's just gonna start light getting bigger then a little bit. It looks like it's not 96% yet. This is pretty crazy to watch, actually, just with your naked eye. Because like, what always happens is I used to always, like, pull out a telescope or a camera and look at it, and you lose the experience, you know?
You're looking
Anyway,
at you're able to see the moon?
yeah, I'm looking at the moon now.
Yeah, I can't. It got covered up by fucking clouds, man.
Yeah, what's crazy is it's cloudy here. There's just, like, a perfect little hole in the clouds right now, but it's cloudy here too. Um, yeah. Yeah, they think I'm so crazy because I mentioned the raw thing from Egypt. But yeah, so anyway, with the thing that I'm talking about, bro, okay, stationary ether is an absolute background, right?
right.
Um, and this just introduces uh, a few different problems, say like Aries failure and MMX. Like if I'm like moving through space, well, I'm actually moving through ether, so
Hmm.
motion is absolute.
Hmm.
Um, which obviously that's a perfectly more logical explanation for all of physics that we do and all of mankind, right? Like that's literally the base assumption we make in all of physics in the lab frame.
Yeah.
So like makes sense, obviously. But when I add motion to it, I should in theory be able to detect it. So then when it gets complex, I may have talked to you about this. I don't know. Um, because I want to think. I feel like I remember you saying that you think there are explanations in tests that get it closer to zero or something. But like the MMX did detect, it did detect a fringe shift. And then when Dayton Miller came and replicated it with like hundreds of thousands of measurements, he found that there was a direct relationship between altitude, the fringe shift increased with altitude, and then there were the maximum and minimum fringe shifts directly corresponded to the spring and autumn equinoxes. So the interferometric measurements were directly correlated to solar motion, right? So
These are
like,
done outside though, right?
do what?
Like the modern MMX ones are done like in a sealed vacuum chamber underground, I'm pretty sure.
Yeah, they and they'll do it like underground, and then they normally like run them through crystals, where they vary the length of the arm. Like they literally like doctor the test to make them match. Like they run them through crystals. One of the most famous ones cited to show that it's close to zero was done in a basement where they run the the light beam through a crystal to make it match the other one. But like, um, what I'm saying is like if you look into what was going on, they were trying to explain like Einstein himself said if Dayton Miller's findings are true, then his entire theory collapses like a house of cards, right? Because experiment reigns supreme. And if it's basically if Dayton Miller's findings are not because of a fundamental error, then um, his theory collapses. But so like the most common explanation for it was like heat, but he went and introduced radiant heat sources directly to the test and showed that it wasn't. And you can see the conundrum here, right? If what he found was that there was a relationship with altitude because it couldn't just be based on heat, it couldn't be just based on pressure, like because the friendship was increasing at higher altitudes with lower pressure. It was changing throughout the year, even at that higher altitude where there wasn't huge changes in temperature and it wasn't corresponding temperature, and he introduced radiant heat sources. So if he finds where he gets to lower air pressure on the top of a mountain, the friendship increases. And then the modern replication of it is to, oh, so according to Dayton Miller, the fringe shift increases when we get closer to the sky. Let's dig underground. You know what I mean? Let's go underground and run the light through a crystal on one of the arms. And I'm not making that up. That's literally what they did. Like when you go to Wikipedia, it'll tell you that as we've gotten better technology, it's gotten closer to zero. And like the main one closest to zero that people invoke, they ran it through a crystal. So I don't know. But I mean, I guess my point here is like you
I
would
think they're trying to
agree,
isolate it from external like temperature and environmental factors.
but it's weird to just
But
do it
sorry,
to one of the light beams, right? Like, and specifically the light beam that needs to be shorter, that needs to
only
slow
just one.
down
All right, I
effectively.
gotta look into what the test was then.
But yeah, yeah, I'll find it in a sec. I'm not certain now. But but you would agree though, like if because what hasn't happened is like tests at varying altitudes. Like I think that we would all agree that isolating it from external factors is good. Now I have heard Pietro was telling me about like while they were just assuming because the refractive index of the air in a controlled environment was like so small that they basically just didn't even account for it. But in reality, it does have an effect, right? And so you would get closer to zero in a vacuum chamber. Um, so
You
I'm
would,
happy to
right?
yield on
Yeah.
that. Yeah, but what that doesn't explain to me is like the varying relationship with solar motion, right? Like the
Hmm.
refractive index of the air didn't change directly related to solar motion, right? I mean, you'd have to invoke temperature.
Yeah.
We would say like basically the temperature changes with the seasons, which changes the refractive index of the air. But the problem is he documented all the temperatures and then increased or introduced radiant heat sources to it, showing that the change is not proportionate to the medium's temperature. So this is the thing, right? Like, I'm not even claiming to know. The test hasn't been replicated correctly, in my opinion, to this day.
Yeah.
Yeah.
Yeah, I don't know much about the details of all the specific Michelson-Morley tests at all. I assume that the modern ones are being done with very precise temperature controls, but I've never looked into it in detail. I guess this would be cool to look more into.
Yeah, see, normally when you do that, when we do that, we end up finding some like major thing that's misrepresented. Um,
Mm.
I'm happy to see new tests. I know we went through all the tests that were listed like on Wikipedia and stuff like that, but I'm
So,
pretty sure all those would be in space audits. Like if you Google space audits Obsidian, you could go there and there's like you could just search for anything.
How about Aries failure? I'd like to hear you guys talk about Aries failure.
Oh, yeah, have you looked into Aries
um,
failure?
I mean, I was reading up on Aries failure. I was trying to understand if there's something about it that's fundamentally different than MMX, then that there's a difference in what it's testing that isn't just again a test of motion through the ether. So
Mm.
putting aside for a second the sort of question about what the quality of the experiments is, because I'm not an experimentalist, so I can't vouch for that. Like going off of
Yeah.
what the official report is, that a interferometer, an MMX interferometer, does not detect linear motion. I think the main point and the interesting point I was bringing up is that while I haven't looked through this for like full scale and all their complexity devices, I've been interested in looking into just the very elementary application of Maxwell's equations of electromagnetism to just two charged particles, just to find the equilibrium distance they will hover near each other, where the forces cancel out to zero, and how quickly one would orbit the other. And you can see length contraction and time dilation affects that factor of length shortening and you know frequency or orbital speed slowdown. If two charged particles are whizzing around each other just based on their motion, just based on the rules of magnetic forces that were understood, pre relativity back in like the 1860s. And maybe this is
Uh-huh.
just me being a theorist in the way I think about it, but like I often, because I'm not an experimentalist, like I look for like as simplified, as shaved down away from extraneous details, examples I can come up with and look through like, okay, what would happen here with the forces between two objects interacting in this way? And, and then I can sort of inductively say, well, if it is the case that reality, that all the physical matter around me is just held together and moving and vibrating based on these types of forces, and I see what happens in a very general case here, then I can, I feel safe in assuming that it would apply to all things of matter held together by forces that behave in this particular way. That's kind of my inductive extension, from the simple case to the rest of the world. But to be fair, I haven't, tested or, this for complicated real world clocks and devices and stuff. The best I can do is try to come up with what could be interesting ways that you could actually like photograph something being length contracted. What would it take to get a high speed photo that shows something being length contracted? Because it's got to be, if it's real, it's got to be real. It's got to be directly observable under the right conditions.
Yeah, because like, look, like, I don't obviously I don't have any issue with that phenomena, right? Like, um, the
It's just
primary
a
building
phenomenon.
will
Yeah.
just like, yeah, I mean, it's just like a real thing, right? Like everything is held together. Like let's just say like all molecular and intermolecular attractive forces are
Yeah.
electrostatic in nature. Yeah, so like if you strengthen that, it'll contract, and
Mhm.
if magnetic strength is relative, it changes relative to motion or velocity, then like logically speaking, objects could get smaller. It would be an insane, this is my opinion, an insane coincidence that what we measure and call time and the length of the material object would change at the exact same factor. I know that I think we disagree on that, but like that's what I think because time is just conceptual, right? Like time is not a real thing. Like it's not an entity. Like uh so Henri Poincaré says it best, right? Who actually created 4D time space geometry.
Mhm.
Um that Einstein used or whatever, he's like, it's not the universe that imposes space and time on us, but rather it's we who impose space and time on it.
Yeah.
Yeah, because we just need to like mathematically and conceptually quantify or understand it to quantify it. But like time isn't a thing, right? And like the problem is though, if I'm moving through a stationary ether and there's an impedance on certainly light, um, that motion is going to cause like a ether wind. And if that is causing a contraction, or basically the ether wind that can be detected, um, directly correlates to the apparatus contracting, right? Then
Mhm.
you have to now invoke time to be a real thing, because time needs to be some like real entity that's being physically altered, in
Well,
direct
I think
relationship to that.
what we could say is that in a stationary ether framework, right, there is a kind of true frame of reference, right? There's the frame of reference in which the ether is stationary. There's a objective difference between stationary versus moving, and there is some time that I guess we could call the true time, which is the rate at which time passes if you are stationary with respect to the ether. And then what you would say is that anyone who's moving through the ether is experiencing like an internal clock slowdown, right? And you could leave it at that. You don't need to say that. We could hold to, okay, there is time is kind of the default rate that things pass by at, and that is defined by there being an objective stationary ether frame. And then there's still the concept of a personal time, like of how quickly any given clock ticks, right? But we would understand that if a clock is ticking slower because it's moving through the ether, this does not change what the definition of time is in the ether frame. This is just saying that that clock is individually undergoing a slowdown of its internal tick rate, its internal mechanical motion, because of its velocity through the ether.
Okay. Yeah. So when I take that and I compare it to like Aries failure, right?
Mhm.
Like you have a bit of an issue, right? Like if there's a stationary ether, um, then in a stationary, okay, we'll say a moving Earth through a stationary ether,
Right.
because you're gonna have to invoke the orbit to explain stellar aberration, right? And so that's like the claimed cause of stellar aberration is that the Earth is moving around the sun. It's in 180 degrees away from each other, 6 months apart, and that's causing displacement of the stars.
Mhm.
And so, like, okay, if we go with that route, like go that route, right? I'm gonna look up at the stars, see the angle of stellar aberration, and align my telescope with it. And then the idea is that the light enters this telescope, comes down to me, whatever we know the angle. When I add a different
Right. You
medium
fill
to
it with
it,
medium and it
yeah,
slows the light down more in that direction.
yeah.
Um,
So we have a prediction for each of them, right? Like
yeah,
there's a ether wind prediction, there's a um, stationary frame prediction. There's a moving orbit with no ether prediction, right? And there should be a displacement, but there's not one.
right. But then we need to bring in length contraction, right? Because when Airy originally did this calculation, he was going to treat the telescope tube as being the same size, regardless of how it's moving. Um, so I don't know. I need to
Oh
like
yeah,
work
well
through
look,
this
look, I
individually.
like you, man. But this is the issue with that, right? Like the telescope is obviously pointed up at the sky at an angle, And so if we're moving through space, basically perpendicular to that telescope, then it would contract like widthwise. So then that's not
Right,
gonna help
right.
us with the duration of time that the light travels through it. So in fact, it would actually make it worse, like, in a way, right? Because it would still displace at a greater angle, but now it's actually just gonna hit the edge of the telescope quicker.
Yeah,
No, I don't think it would actually I'd have to do the
I need
math,
to
right? It just
yeah, I need to
probably
do
wouldn't
it as
actually hit
well,
it.
but that's my thought of just like, okay, well, the thing is, if it's tilted, if the telescope is tilted relative, it's not fully perpendicular, it's not fully parallel to the direction that the Earth is moving, and the contraction only happens in the direction of motion, then the contraction happening, it's actually going to change what the angle of tilt is. Uh, in terms of absolute space, if you contract its length one way but not the other way. Um,
That's true, yeah.
I don't know, but I don't. I need to work through
I
it
don't
in
know if it would
detail.
change it the right way though. I don't
I mean, that's I can't say one way or the other without explicitly checking. Yeah, but that would be bad if it went the wrong way. I don't know.
Yeah, I mean, from my understanding, when they were trying to work like an ether into it, that is, it actually did go the wrong way. Um, like, because they tried to explain, Earth moving and still invoking an ether to explain Aries failure. I mean, this was before MMX, right? So they actually desperately wanted to hold on to the ether. But you also have
Mhm,
like um just James Bradley in and of itself, like right with the raindrop effect or whatever, like stellar aberration. Um which is where, he discovered that we have to tilt our telescope slightly forward to catch the light of distant stars, depending on what season it is. Um, so, like, exactly how you have to tilt it, it would be like akin to like rain falling, and if you're
Yeah,
walking through it, you tilt your umbrella, whatever. Um, so then there was this idea, right, that like if there was a stationary ether and the Earth is moving through it, it would basically drag like a little bubble of ether with it, basically.
yeah.
And, yeah, they called it, like, ether drag, and then that the ether would kinda straighten out before it hit the telescope, like erasing stellar aberration, uh,
I was watching some
but cut
videos on it because I never studied or thought about Aries failure before, so I was catching up on like, okay, wait, what is it that they're saying was supposed to happen here? I don't know. I guess I didn't do much optics in school, so
yeah, well, I've never even heard of it, right? I don't think the average person's ever even heard of that test. Um, I mean, I've never even heard of MMX, but to be fair, I didn't go to college for physics, right? Like I did, so maybe that's where you would hear about some of that, but I don't know. Like, I think that most people have heard about it. If they've heard anything about Mickelson Morley, it's like Neil deGrasse Tyson calling it the greatest failed experiment ever and whatever. And
yeah.
like, yeah. But these are so the thing is like I guess the meta here, right, is like any fundamental shift due to the current discoveries of quantum mechanics, which by the way, they're way behind, right? Like it isn't like we just discovered this stuff yesterday. We discovered it decades ago, right? And we've been discovering it ever since. And each subsequent discovery just further supports and like
Mhm,
validates this like permeating medium, right? Like it's
mhm,
inescapable, but it actually has been for a while. And like the reason I think that it hasn't just been integrated in is because you need so many of these relativistic explanations for these early tests that got us to where we are. So basically, you like it would require like swallowing your pride and going all the way to the drawing board. And what it automatically does, like immediately, is it puts like a stationary Earth on the table, and then we could disagree about whether or not it is exclusive to that or if another explanation could be. But while you're sitting here and you're attempting to explain and I applaud it, like the average person in these fields is not going to do that, right? It's just way too risky, bro. Like if there's not like a community effort, a community acknowledgement of a shift, that then we're going to all go look at these different tests and then do all the subsequent tests need to be done to verify any possible alternative theory where the Earth can still be moving, but there is a stationary ether or whatever, and which is like in my opinion, ultimately going to prove to be impossible. But like, they're just not realistically, they're not going to do that. Like the obvious explanation in all of these tests is the Earth not moving, right? Like if the better we refine MMX, et cetera, if there actually is no fringe shift, the painfully obvious explanation is that the Earth's not moving, right? Like, so
Well, I
on its
mean,
face, good.
I mean, with anything that fails to see motion, you have to go and ask, well, does it make sense that this should have been able to detect motion in the first place? And like, I sort of get it of like, well, isn't it obvious at some intuitive level that if we don't detect motion, there was no motion? It's like, maybe, but I don't think that's really like a great criteria there as far as like,
Well, no, I'm just saying like
what
it's
intuitively feels
well,
obvious
more
or
so I'm
not.
just saying like it's viable, right? Like the obviously a potential explanation for it is like the Earth not moving. Like this was even known back then, right? It was like basically we got to this like cornerstone where they were like, okay, either the Earth is stationary or um we have to throw the ether out, right? And they proposed multiple theories to try to keep the ether because it was like unthinkable to throw it out. But what was even more unthinkable was throwing out the motion. Like it was considered to have been proven, and so it wasn't even on the table. So then we just have people proposing different variations of ether theories. Like up to that point, Newtonian mechanics and an ether theory was assumed to be true by
Yeah.
effectively like all physicists, you know. So you would have got the same pushback like when Einstein went into the Royal Astronomical Society for the first time, he got like laughed out of the room. Like it was just, we know this works, it works for all these things, basically a giant pragmatic fallacy or whatever. All electrical field theory. Maxwell's equations are built upon the assumption of an ether. Like everything that we use, everything that like that built our electrical grid we use today, like it's all built off this fundamental assumption of an ether. You know what I mean? So like then they just kind of
Yeah,
took that
yeah,
out and they
Maxwell
kept
was
all the equations.
entirely. I mean, it's not hard to see why. If you just look again at the force equation for the magnetic force, it depends on the velocity. So we have a force that explicitly depends on the velocity of an object. Well, velocity with respect to what? I
Yeah.
mean, it's sort of impossible to teach magnetism, initially at least, from any standpoint, saying that there's a preferred reference frame, that the electromagnetic field is a medium like any other medium. It's got a rest frame. The velocity that goes into the velocity variable in the equation that references velocity is the velocity of a charged particle through that medium. It's like, how could you have velocity as a variable in an equation without it being in reference to something objective? Um, and that is 100% how I, you know, uh, teach introductory magnetism. Um, and it's a valid and workable framework. Um, the twist is, though, that because the forces that hold matter together depend on velocity, now interesting things happen to matter as it moves through space. And my suggestion here is that these effects, which can be explained as kind of just real physical phenomenon of the electromagnetic force between the atoms within an object, as it moves through the ether, through the fundamental medium that the electromagnetic forces come from, that there isn't a way of intrinsically detecting that linear velocity through the medium because of the very features of these force equations that explicitly reference something's velocity through the medium, like the fact that the magnetic force depends on the motion of a charged object immediately points to a conceptual framework of a charged particle moving through a medium, and that's what gives meaning to that velocity. But then because these forces depend on its velocity through that medium, it makes it impossible to actually detect its velocity through the medium. Because any way of trying to detect the velocity through the medium is distorted by physical changes to the object by the scaling of these forces that occur as it moves through the medium. So kind of like the whole topic closes in on itself um, in this interesting way where
Yeah, I mean, the part I keep losing you is just like the idea of like different sizes of different material compositions would all change the same amount of like.
yeah, yeah, no, I think it's definitely extremely non-intuitive.
I mean, I think it's intuitive to think that like the variance in like strength of force, like the force
Mhm.
strength would change. Like that makes sense, right? Like that would
Right.
change the same, but just
Yeah,
like
but then
that
it
it
would
wouldn't
scale
change
everything
everything the same.
evenly.
Yeah.
It would change the thing made of wood and styrofoam and iron and hydrogen gas, like whatever. Yeah, no, that's extremely.
Yeah.
I don't think that's an obvious conclusion at all.
Yeah. The other thing is like even the idea of a curvilinear velocity of the orbit, like the way that we're because the Earth is not moving in linear motion, right? Like it's actually moving around the sun.
Yeah,
So, like, the way Einstein got out of that was by saying, "Oh, well, there is no actual absolute reference frame to measure motion against, and the only absolute that we have is light, and that's gonna always change relative to reference frame. So, for intensive purposes on the Earth, we're free falling, and we're not ever gonna be able to detect or measure it because everything that we would use to do that is being evenly affected by the motion," which is fundamentally the same claiming this other idea, right? But the difference is the mechanism, which I mean, relativity doesn't even offer one, so it's not even considerable in my opinion. But like, but that doesn't. I don't see how that can work, right? Like, we can't have the whole we're free falling through the curvature of space if we have like an actual stationary background medium because what we're actually doing is measuring motion relative to that. So that motion is going to be it's going to be measured relative to that, even if we're going around the sun, even if we're going through space. This adds a whole nother different variable, which they didn't even know about at the time of MMX, which is that you should have also, in theory, been able to detect the supposed motion of us through our galaxy. It
yeah,
shouldn't have just been the motion, right? So we're actually going to have compounding motions that would so in this other idea would be affecting the magnetic strength of the objects in different ways. Like Lorentz didn't even conceive of that, right? Because at the
no, yeah.
time the model didn't even include it.
Right. So after addressing the question of, well, what happens to something that has constant velocity, and is the constant velocity detectable given what we know about the forces that exist within matter? Then the next question goes, well, what about acceleration? Um, acceleration should be detectable, and the Earth orbiting the sun isn't just constant velocity. There is an acceleration because you're going around in orbit. Um, okay, so Einstein does have this whole interesting interpretive framework of the bending of space and time. But what's at the heart of that is the fact that gravity is supposed to work the same on everything. It's like you can hold on to the idea of gravity as just like another field, like the electromagnetic field. But whereas the electromagnetic field would push a positive one way, pull a negative another way, gravity is going to pull on all things by an equal amount, which doesn't feel that strange to me of a concept of a force field that happens to be sort of calibrated against matter and such that it pulls on all things at an exactly equal amount. So if it does pull on all things at an equal amount and a whole collection of objects being pulled by gravity move together, so there's no kind of relative motion between them, and you're not going to feel any strain inside your body as you're being pulled by gravity because every part of you is being pulled by the same amount. And that's where Einstein starts saying, like, okay, this makes free fall the same thing as just inertial straight line motion and he starts importing all of those ideas um, into it as well, which maybe we could take a step back from and reject the whole kind of framework of saying it's warped space-time and just saying that the gravitational phenomenon is another force field, but it's one with the kind of unique fact that it pulls on all things at an exactly even rate. And it doesn't just affect matter, it also affects the electromagnetic field. So it's another field that affects the electromagnetic field in addition to affecting matter. And that's why you're not going to be able to directly detect a constant acceleration free fall in a gravitational field. The one thing I'll say at the end of all this is that it does sort of kick the can just one notch down the road, and that if you dig into the details of it, um, while Einstein's saying that yes, in addition to linear motion, you also can't directly detect gravitational free fall acceleration, you can detect changes in acceleration. So the thing that is detectable is just pushed one more order back from acceleration to the rate of change of acceleration, which is called jerk. So that should be detectable. So we should be able to detect on an interferometer, according to the standard theory, while the interferometer can't detect the linear motion and it can't detect the rate of change of the linear motion, being the gravitational acceleration, it should be able to detect the jerk, the change of the acceleration. You definitely need an extremely precise machine to try to do that, though.
Yeah, because but there would technically be there, yeah. But
But it
so
would technically be there. So this is a falsification point, right? This is
yeah.
a thing to look for confirmation or falsification of the prevailing theories as they stand, because the jerk should be detectable even if the acceleration is not.
Yeah. So then, like, in theory, um well, yeah, because, like, the other issue I see here, right, is, like, the Earth is moving, so, yeah, it's spinning, allegedly, whatever, and then it's also
Mhm.
allegedly going around the Earth, but it's also going through the galaxy, and then the galaxy is also going through space, and so we're getting into, like, insane velocities, right? We're getting into, half a million miles per hour through the galaxy, 1.2 million miles per hour through space or whatever. So, like, if I was gonna take the Michelson-Morley, and they didn't even conceive of those things, there's 66,600 miles per hour around the, um, 30 kilometers a second around the sun.
Mhm.
So, like, this is gonna here, let's look at Lorentz equations. Okay, here, he basically just like made that work, which I mean, he was pretty brilliant. So whatever, we get this amount of change, like this amount of contraction. Okay, but now if I add this other variable, the directional component changes, the velocity component changes. So thus it has to change the net effect, right? Like the contraction, especially through like a
Yeah.
stationary ether.
Well, oh, yeah. So, okay, yeah. So within the stationary ether framework, every component of velocity causes a contraction. So obviously, the motion through the galaxy is at a much faster speed than the motion around the sun. So there's an even greater degree of contraction in that direction than due to the velocity around the sun. But, the argument I'm making here is that it doesn't matter what the linear velocity is, the contraction is what cancels out your ability to do the type of direct detection that Michelson Morley were hoping to be able to do. Um, so, no linear velocity is going to be, you might be able to see it from the outside, but intrinsically detectable. But these kind of higher order properties of motion, not the velocity, but the rate of change of velocity, or rather the rate of change of the rate of change of velocity, should actually still be directly detectable using some type of interferometry setup. So yeah, some sort of interferometry setup should be able to detect these rate of change of motion due to the orbit around the sun and the orbit around the galaxy and all of that.
Yeah, I guess I'm losing you here actually, like, cause like, um, yeah, like when you manufacture the test of MMX, right? Like the only velocity considered is the velocity of light and then the velocity of the orbit. And so
Right,
then
yeah,
we
sorry, so
we
not an exact MMX, right? Because that's only set up to try to detect a velocity. But something like Sagnac is detecting um, by detecting rotational motion, because when something's spinning, one part of it is moving in the opposite direction as the other part. Like when a wheel is spinning, the top part
Mhm.
of the wheel is going one way, the bottom part is going the other way. So what makes Sagnac fundamentally different than MMX is MMX is looking to detect a singular linear velocity, and Sagnac is able to do a detection of comparisons of different velocities, like going around the loop one way versus, going around the other, or the velocity of the loop going one way versus going the other way. So yeah, so it wouldn't be MMX per se, but I just mean, um, I don't know what it is, but there is some sort of interferometry setup that would be designed to pick up the the jerk, the rate of change of the velocity of the Earth as it moves through space. And then all of these motions, motion around the sun, motion around the galaxy, would have to be detectable, by such a
Well, you would
machine
have to set
for
up like
it.
a layered interferometer that has
Yeah.
like different orientations relative
Yeah, I
to
don't
those
know
motions.
exactly what it would need to be much more complicated than MMX, because um you'd need to be doing a lot of more different comparisons of things to extract out from that information about these um rates of change of velocity as opposed to just the velocity itself. So I'm not entirely sure what the setup would be. But just like in principle,
Yeah. And I
this would
mean,
be
look,
this
man,
would be an
we.
interesting thing to look for.
Yeah, and obviously no hard feelings if we disagree. I just think we do like I think we disagree a bit. Like I don't like I
Well,
do
yeah,
find it interesting, but I think that MMX is like what I mean specifically is that it would have still been affected by those alternative motions, right? So like if it was just so happening to contract just the sufficient amount to explain the orbital motion, well, it would have actually contracted in a different orientation at a different rate and a different amount. And so like even if we couldn't like specifically detect it if we're oriented within there's linear motion, but we have conflicting motions. So like that net contraction is going to be affected by that other motion, right? Like because it doesn't matter. Like if in fact it's going to be affected more because we're just moving faster because the magnetic force doesn't care uh what orientation we're doing anything. It's just like it's just experiencing motion. And if it's experiencing motion this way at this speed and this motion at this way at this velocity and then it's just going to be increasing and thus contracting relative to those velocities and directions, right? And so it would be pretty complex math. Like I heard a guy, I believe he's like a professor at Harvard, and he actually gave a presentation on this explaining that like a major thing that people have overlooked at MMX and even consider us flying through the galaxy. I didn't even know about it, but like the math is pretty complex because what you're getting into is the time of year that we're in the orbit and what's the relative orientation in relation to the assumed motion through the galaxy, right? And then you have to actually do the math of the differential between those two orientations and velocities. You're now going to add another one where the whole galaxy is going through there. So my point is like just what you wouldn't get out of all of those compounding things if they're all affecting the internal
yeah,
components in the sense of like the fundamental mechanism that holds it together is like you wouldn't just get the exactly sufficient change that is expected by the 30 kilometers a second. But unfortunately for them, and this is just kind of how truth works, right? Like truth always ends up coming out. Like they didn't know about that. They didn't know that their model was going to incorporate these alternative or additional motions. So when Lorentz did the math, he just took the 30 kilometers, knew how much it needed to contract, and said, okay, it contracted this much. Right. So, but now there's a whole variable he didn't even know about. Like if Lorentz
you
had,
mean the
if
motion
he,
around the galaxy?
yeah, like Lorentz would have done a different equation, in my opinion, if he knew about that.
Well, no, I mean, but it's just based on I mean, like whatever the velocity is, it's like the amount of contraction is just dependent on what that velocity is. Like, so I'm not really following why you're saying that, like, oh, because we're also moving around the galaxy, that all this dramatically throws it off. Like, no matter how many velocities you have, like, they all just sum up to some total velocity. Um,
But the
and if the
contraction would be different, right?
You mean as it, yeah, if the contraction of
Like
all
the net
that is
contraction or
caused.
whatever you.
Yeah, yeah.
Yeah,
But it's
that's what
like,
I'm s
but the point was that the contraction is what disguises any fringe shift effect, right? So it's like,
Well,
right, that was
only because supposedly it contracted just a perfectly sufficient amount relative to the orbit of the Earth, right? So, like, we got a fringe shift, we assumed it was an error, said it was 0, and said, "Okay, we were supposed to get this amount of fringe shift," but it contracted that exact amount because we're moving and orienting it based on that velocity around the sun. Then we, of course, threw out the absolute space and said that there was no absolute space. It was all relative reference frame dependent. That's so we could incorporate the claim of it being linear. And so, because we needed it to be linear to explain why we couldn't detect it. And then we also had to contract the apparatus. But like, I guess my point is like, yeah, we get that perfect sufficient amount, but it's just because the input is the orbital velocity. But like, if we didn't change anything about Michelson-Morley and we just did it again right now, knowing what we know, it shouldn't just be the orbital velocity that contracts it. It should be these other variables, which would change the net contraction. And it wouldn't be as simple as like an additional, like addition or anything like that, right? Because it's going to be relative to the orientations, right? Like if the apparatus is aligned and oriented based on where we're at in our orbit, our supposed orbit, well, that's not going to like just perfectly add to where we're flying through the galaxy. You could probably pick like a ideal time of year to you could orient it to either
but I
compound or even subtract. But I don't see how you could just like they wouldn't do that. I feel like it would have to you'd have to account for all of them and then it would change the net contraction, right?
yeah, but I'm not really sure I'm following what the point is because the experiment is a null result, right? There's a prediction for what the fringe shift should be based on the velocity of the Earth. We don't see the fringe shift. So then you can find out, okay, how much contraction would be needed to cancel out the fringe shift that would have otherwise been there based on its motion. So of course, Lorentz first thinks to calculate how much contraction should be there to cancel out the motion of the Earth going around the sun, and he wasn't thinking about the motion around the galaxy. Um, but if he had been thinking about the motion around the galaxy, then he would have calculated that, okay, it must have been this value, right? It's like, it's not like the contraction was something he directly observed. It was just something he was calculating of how much contraction would need to be there to cancel out a given
Well, yeah, of
amount
course.
of
Of course.
allowed the fringe shift that would have otherwise been there based on its motion. So, of course, Lorentz first thinks to calculate how much contraction should be there to cancel out the motion of the Earth going around the sun, and he wasn't thinking about the motion around the galaxy. Um, but if he had been thinking about the motion around the galaxy, then he would have calculated that, okay, it must have been this value, right? It's like, it's not like Lorentz first thinks to calculate how much contraction should be there to cancel out the motion of the Earth going around the sun, and he wasn't thinking about the motion around the galaxy. Um, but if he had been thinking about the motion around the galaxy, then he would have calculated that, okay, it must have been this value, right? It's like, it's not like the contraction was something he directly observed. It was just something he was calculating of how much contraction would need to be there to cancel out a given
Well, yeah, of
amount
course.
of
Of course, yeah.
velocity dependent fringe shifts. So then what I'm saying is whatever the total velocity is, no matter how many velocities you
It
add
would
up
always
together,
work.
yeah, there's some total velocity they all add up to, and then the actual contraction is just in the direction and to the magnitude, you know, to that total velocity.
That's what I'm saying, those
The
are gonna
prin-
conflict, right? So,
the
like, the
principle would
apparatus is gonna
apply.
contract, it's say the length of the apparatus is gonna contract if it has an eastward orientation. We're moving through the
Yeah,
galaxy south. So then, like, the magnetic strength is gonna increase, contract physically contract that apparatus east, right, according to the orbital velocity, but simultaneously, it's gonna be contracting
yeah,
basically an angle perpendicular to that, so like a width, right?
sure,
Like, they're
yeah.
gonna
You
be
know,
different.
you're moving a bit this way, you're moving a bit that way, um, so you get
We're
some
moving a lot
contraction.
that way. We're moving a lot the other
Yeah,
way,
all
right?
right.
Like, yeah. I'm just saying, like, so then don't you see that? I guess the way I see that is like if I increase the field, to say I increase the magnetic force, right? Like left and right, and
Mhm.
then and this is kind of crude, right? But I increase it left and right, and then north or and up and down, I increase it 10 times more. Well, then
Yeah.
that's gonna affect the contraction left and right.
No, I mean it's what I'm saying is that the amount of contraction in any given direction has to do with the scaling of the forces in that direction, has to do with the total amount of velocity in that direction. I mean, like
Mhm.
force and velocity in one direction are independent from force and velocity in a different direction.
Why? I mean, like, yes, I understand that they're independent, like they're their own independent phenomena. But when we look at the net effect, if we just have one object, there's only like whatever. Let's just call them atoms. I don't believe in those, but I think the phenomena is real, so it doesn't matter. Like, we'll just say that the atoms, and they have like um, an electrical relationship that increases proportional relationship. So also magnetic, right? Those you can't really throw one or the other out. So it doesn't really
Yeah.
matter. So it's like, okay, so they're contracting based on the velocity and the direction. So imagine like I'm just envisioning like taking my hands and I'm pulling them together, right? Because they're being brought in together. If another force that's even stronger is actually pulling up in a perpendicular direction, as these are coming into each other, they're actually going to be deterred or like retarded would be the actual term, right? Like because there's a different directional force acting on it simultaneously. So it's like they wouldn't go together at the same rate, and they wouldn't have the same net contraction. In this situation, yeah, you would think like whatever the orientation of the galaxy is so much higher velocity, it would largely outweigh the orbital contraction, right?
You're saying that if two things have a force pulling them together along like the left right direction, that's going to be affected by if there's also a force pulling them up in a perpendicular direction. I don't think that's the
Mm,
case. I mean,
yeah.
um, yeah, my understanding
I
of
guess I could be
force is
wrong. I
that
just
force
don't understand why it
with
wouldn't work that way.
yeah, that a force in one direction has no bearing on a force in another direction. That forces and the effects that they cause in each direction are happening. Um,
Mm. But do you agree
yeah,
it's the
just
same
or
force?
separately,
So technically, it's the same force. Like
but the
there's
same type
just
of force. Yeah,
well, okay, that's where we're disagreeing. Like I'm saying, they are the same force. So you're saying there's like an additional magnetic force that's being affected by the different motion because, like, let's just use atoms or whatever. You have the atoms, they're being held together by a force, and that force is
yeah,
being affected by velocity. So like
yeah,
whatever velocities you add, they're all affecting that same force and giving you a different net outcome,
yeah.
right?
Every new component of velocity you add to the object generates a proportional new component of force within the object. Yeah.
Right.
So
And those would be
it would just
different orientations.
yeah, and in different
Right.
yeah, because there's explicit orientation
Yeah.
to the direction of magnetic force.
Right.
Yeah, so a charged particle, if it's going to the right, it's going to feel I forget which way it goes, but this is the right hand rule. Yeah, wait. So a charged particle going right feels an upward force, and going up feels a leftward force. But each type of velocity it have will just independently generate, you know, its amount of force on the charged particle. So that's what I'm saying about just like
Mhm.
these effects could just stack on top of each other.
I don't know.
I mean,
Just
not
keep losing
intuitive
me
that
there.
that's the case.
I mean, maybe I'd have to test this. I don't know. Just yeah, it doesn't make sense to me, but I don't, maybe. Um, yeah, it would. Obviously like so like I like you. I like to have good faith conversations,
Mhm.
right? So like this is interesting to me, but like obviously on its face, it's like a unfalsifiable premise that's just conveniently untestable. So like I do appreciate the idea of trying to
No,
introduce falsifiability to it, right? But
yeah,
like
I've given a couple
it's
of falsifications because what I've said all this leads to is that um, even though velocity and free fall acceleration aren't directly detectable, the rate of change of acceleration should be. So if we could figure
Mhm.
out how to build an interferometer that is sensitive to that, then that should be able to directly see that aspect of the motion of the Earth. Because if the standard model of physics is correct, it's not just that the Earth has a given speed at a given moment of time, but that speed is changing as it goes around the sun, as it goes around the galaxy. What I'm saying is that we need to target trying to detect that variable, not the speed itself, but these rates of change of speed. And if those tests failed, then that would prove that the Earth is not moving through the universe in the way it's claimed. I'd be interested in trying to figure out how one would set up a test like that. And then the other thing is that i- the type of physical contraction that could perfectly hide the linear velocity interferometry fringe shift, right? The type of Lorentz contraction that's needed here so that you don't get to see an effect of the velocity on the fringe pattern in any type of a setup like this. And so that everything contracts together in the same way, no matter how many different components of velocity there are, no matter how many different components of velocity you add up, so that it would not be intrinsically detectable, like if you are the one who's moving. This requires um, very specific features of forces. Like this only works given some really particular features of what the electromagnetic equation is. And it also requires that all other forces in matter need to obey these same properties. So if we found any force that did not obey these properties of how the force scales with velocity, then that would come, yeah, completely um, destroy the entire framework, that I'm describing here, or at the very least, the better way of putting it is that if we discover that there is a force that in any way does not depend on velocity in the very specific way that the magnetic force does, then immediately direct detection of linear motion through the ether is back on the table and should be possible.
yeah, so I think so I think our fundamental well, for one, I would say like I think that the all interferometers should be able to detect that. Like the change so like the acceleration is a change in speed and then like even if you broke it
Yeah,
further up into like the relative changes within that, so the changes within the changes, right? Like
yeah.
um in theory like interferometers detect that all the time. Like that's like what they do. You know?
Well, I think the fringe shift was supposed to just be proportional to velocity, right? So I don't know off the
Yes.
top of my head how to create something with an observable shift or something we could just look at that should be, directly proportional to
Well, basically, the
these.
way that they viewed that is that just that as they do the test throughout time and slightly shift the orientation relative to the orbit, they should see a corresponding fringe shift adjustment. And so all those
Mhm.
small, like a lot of people misrepresent this test and they'll say stuff like it wasn't sensitive enough. Da, 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 da. Like it absolutely was, right? It was like 20 times more sensitive than it needed to be. But then Dayton Miller comes along and it's way more sensitive. They're measuring like within 1/100,000th of a wavelength, like plenty sensitive enough to detect like any variation, which is what he did. He mapped out the variations. He found it changes relative to altitude and solar motion. If you change within relative to solar motion, it's very interesting, right? Because like one could look at that on its face and be like, oh, well, that makes sense if we're moving around the Earth. But the problem is we're not supposed to be able to detect it at all, so we can't invoke that explanation, right?
Mhm.
But um, yeah, so I think anyway, that's like so there's one of my things that I'm like I feel like just in theory it should already be detected. But like setting that aside also like I struggle to grant you the linear motion claim. You know what I mean? Like I don't know that I get the idea like a
I just want
gravity
to make.
acting
I'm
on
just.
all matter in the same direction, but like I don't see how that
Yeah,
gives
yeah,
you any linear
yeah.
motion.
I'm wondering what you see as kind of the major um, sort of failure points, what I'm saying, and a couple of them that have come up is that you're not sure you're willing to grant the idea that all objects, regardless of, their specific material, would undergo this um, electromagnetic length contraction in
At the same rate.
the exact same rate as each other, exactly enough to cancel the fringe pattern. And then the next question was, why should you grant a priori that gravity would act on all things regardless of their properties identically, such that constant gravitational acceleration would similarly not be detectable, because everything would just be moving in proportion to each other. And then the third thing was, why should you grant that the effects of velocity, that this electromagnetic Lorentz contraction that is dependent on velocity, is going to sum properly when you add together multiple competing different velocities, like the Earth's
Yeah.
orbit around the sun plus the galaxy. I'm just repeating just to make sure I've properly understood the sort of specific points where you're being like, wait a minute, I'm not sure I'm willing to just grant that. Is there any other major ones that I might have missed there?
Well, it's a slight like even I'm like even willing to grant intensive for intents and purposes the idea that there's a force akin to gravity that acts on all matter the same regardless of the matter.
Mhm.
Like, I,
Yeah.
I have like a somewhat similar framework. I don't want to get on that, whatever. Like I have my own idea about it, but like even granting
Yeah.
that, I failed to see where it gives us the linear motion assumption specifically, um, because it's not.
Well, that was about acceleration. Very sort of specifically, because if you just look at electromagnetic theory, you can reach this conclusion that um, eh, matter would not be able to directly detect its own linear motion through the electromagnetic field. Um,
I agree with that.
but immediately you also get the conclusion that acceleration should be directly detectable. Um,
Yeah.
and this is observed because and this is also for me why I like to think of the electromagnetic field. I think in a very similar way to how you think of the ether, because if you accelerate a charged object through space, it radiates and it experiences essentially a friction force, um, called the back reaction, um, which is basically a friction between it and the electromagnetic field. So it's not a velocity dependent friction, it's an acceleration dependent friction between a charged particle and the electromagnetic field. And to me, that's what makes thinking of the electromagnetic field as a real physical substance make a lot of sense to me philosophically.
Yeah, I mean, I would say I
Um,
don't know how there could be an alternative. I didn't even know that.
yeah, yeah. It's just the radiation of a uniformly accelerated charged particle. Big topic in physics, right? So one of my big points about the whole discussion of Nicholas and Morley is I'm not saying that motion is fundamentally so relativistic that there's no definition of it. I'm just saying, like, okay, maybe a charge can't detect its linear motion, its velocity through the ether, but there's a clear effect of its acceleration through it. That is, unless the acceleration is gravitational free fall. See, if the acceleration is being caused by like launching an object with a spring or a rocket, then an object being accelerated in that way radiates. But if it's a free fall gravitational acceleration, it doesn't. So
Mhm.
that's where Einstein brings in the whole idea of warped and curved space. Though I think a more eloquent explanation is to say, okay, if there is a field that happens to have the property of acting on all matter and all other fields in the same way, then the gravitational field, even though things that are falling seem to be accelerating, they're all accelerating at the same rate, and the electromagnetic field itself is falling with them, is what you'd have to say. So that they're still, can feel like they're at rest with regard to the electromagnetic field around them. If the so now we're actually beyond a stationary ether framework. Now what we're
Yeah.
saying is that gravity is a physical waterfall effect, um, of the ether medium that falls at the same rate as the matter within it, and that's why a free falling charge doesn't radiate, uh, even though, if it's accelerating through the electromagnetic field, it would. Um, so I'm sorry, it is getting a little late, and I might be losing track of where I started in
Oh,
all of
you're
this
good. You're
here.
good, but
Oh
that's
yeah,
like
just saying.
that's a big thing right there where we just got right because like is the whole like what's the distinction between the field and the ether? Is the ether falling with it? Is the electromagnetic field falling in relation to the ether? Because if we start to remove that, then we remove the preferable absolute frame, right? I mean,
Um,
but yeah,
Right. So if you say that gravity is a local flow, right, of the ether, local waterfalling of it, you then have to zoom back out to sort of a larger scale to get back to a preferable frame where you say, okay, even if locally there's these kind of individual gravitational waterfalls of ether that things get swept up within, and that's what we call free fall. um, at a cosmological level, there's still a preferred reference frame, for the entirety of the ether, the entirety of the fluid. There's still a preferred kind of reference frame container where it is on average stationary, where the bulk is stationary. And then what we call gravity is just a very small in the scheme of things, localized uh, kind of area where it's rushing in towards a some sort of central point.
okay, yeah. I mean, yeah, that's kind of crazy to take in, but yeah, man, I won't. I mean, I won't keep you forever, man. Like, yeah, I think you pretty much summarized them, right? Like the different material composition having the same net
Yep.
effect of the physical interaction and contraction. This idea of kind of just granting the linear motion, or then kind of flipping it over to an acceleration, where then the ether's no longer stationary. So now we have like a compartmentalization of ether within the ether that's moving relative to the Earth, and then obviously the idea of like the compounding vectors and
Yeah.
how they would give you the net effect or alter the net contraction. Yeah, but I think it's interesting conversation, man. I think that anything in that realm is it puts forth the idea of the Earth moving in a significantly more viable manner. I would just say that the word "more" is doing a lot of lifting, or it's just
Yeah. I mean, I'm
relative.
not. I mean, this is late night spitballing here.
Of course. Yeah, it's cool.
No. The reason I want to list out the bullet points that you were like, okay, well, I shouldn't have to take that for granted. It wasn't is to be like, oh, okay, and now let me prepare my argument for why
Of
you
course,
should.
yeah.
No, it's just like, yeah. I mean, you shouldn't. It's like these are my
Of course.
own sort of musings and meditations on trying to take sort of what I know about physics and find what to me feels like a more satisfying, more physically sensible conceptual framework to ground it in. And sort of just thinking out loud through, um, I don't know, how could things work to sort of reconcile different streams of thought that we're discussing here, and then sort of what are the further logical entailments of all of that. And we've definitely gotten to a very interesting and colorful speculative vision, of a universe as I described it there, of it's sort of a background ether type fluid, but one that has its own concept of a local, waterfall velocity, which is then um, these deviations, kind of from the background average is then what we call gravity. I guess that's what it would be within sort of where I've speculated to for now. Um, but
Cool.
yeah, it's all just yeah, sorry. Yeah, but it's all just talk. I mean, I'm trying to inform it as best I can. Um, but I don't think it's easy fundamentally to kind of arrive at any philosophical or any sort of interpretive framework. Though, I would say within what I've described, I have laid out reasons why I don't take something like Michelson-Morley as this clear conclusion of the Earth being stationary for all of the reasons I painted out here within this, you know, um, framework that I've been describing. That
Yeah.
seems at least
No, I mean, that's cool, man.
level
That's cool.
to me.
Like I obviously I'm all about the Maxwell's equations and everything's electric and magnetic, and it's obviously
Mhm.
fundamental building blocks. Yeah, 'cause I mean, I did a similar thing. I did a similar thing before. I ran into like a few roadblocks. We've talked about some of them, but yeah, because it's like wait, is the ether moving with the earth? Is there like a little bubble around the earth that moves with it? And then all of the local phenomena happens within there. Are we experiencing motion within like that bubble of ether that moves through the fundamental background, right? Like, is it, because then you get into like this idea of like a non-Cartesian, whatever. I've tried to think about it. I will say this has like been very refreshing conversation for me, because normally when I've tried to kind of walk through that, like, well, yeah, it does necessarily imply these things, or like, well, let's talk
Mhm.
about the implications of what they would mean if you did try to keep the ether. I normally get like a lot of um pushback, you know what I mean? Like, where we don't make any progress, because I'm not claiming to know all the answers, man. I just
Mhm.
know that it would change. It requires changing a lot. Requires going back to the drawing board, at the least, you know.
One sort of subtle but interesting point you brought up is this question of you when you were like, I'm not taking it for granted that multiple compounding velocities are just going to add up in this super simple way, where the whole is just another velocity, and that this will also track evenly for forces and physical effects caused by those forces. And it's like, no, I don't think anyone should take that for granted. That's definitely a kind of deeply non-intuitive claim. And I'm thinking a lot about it now of just like, okay, this is an axiom that we take within physics. This is standard physics treats the world as such that velocities, forces, all these types of quantities do just stack on each other in a very simple way. But it's an interesting thing to interrogate, of like, do we know that for sure? How would we prove that for sure? Or is it just a kind of an axiom of the paradigm that we assume it works that way? So then we look at models in which it does work that way because that's what our prior was. But I don't know. How do we know for sure that that's really how things work? There's a lot of pressure points. There's a lot of interesting pressure points that you've brought up here. That you could push on, um, eh, both to sort of interrogate what is being assumed, both within what I'm saying, and what the standard cosmological framework is, and I guess to maybe leave this at something. It's just that it is. I find it very interesting to look for where these points are where um like if this subtle assumption turns out not to be true, then the rest of the Jenga tower all falls apart. What would the implications of that be?
Yeah, yeah, man. Well, it's a good convo,
Yeah,
brother.
yeah, great. I hope it. I really be taking a lot of time, so I only want to be conscientious to open it up to others who have things on their mind, and also I gotta go sleep at some point myself. But yeah, thanks, dude.
Yeah, nice talking as always, bro.
Yeah.
Yo, Gio, can I talk to the demo? I don't
And
think
thank
I'll
you to
talk to you.
Austin and Zizi for that exchange. It was pleasant to listen to. Thanks for your time, guys.
Yeah. Did someone say can they talk to Denmark? I haven't talked to Denmark in so long, bro.
I tried like 2 weeks ago. It was pretty fun. So hopefully he can be unleashed.
Yeah, I want to talk to the guy. All I could say was 4-letter word with an Z in it the whole time, but we might as well try to get past it. What's it? Are you done with your? I guess you
Oh
were.
yeah. Yeah, I mean, I don't
You're
like,
talking.
I think the
Okay.
ball's in your guys' court, right? Like, I think he's doing you guys a lot of favors trying to actually figure it out. But mind you,
I
like,
mean,
he's not alone, by the way. Like, I have conversations like that, not on a super regular basis, but, like, most people that kind of are looking at a lot of the stuff we're figuring out, like honestly, it's pretty accepted from my experience, like across the board, that there's like we're at the least on the precipice of some major shift, right? Like anyone I've talked to that's like kind of in the field of say like physics, whether it's quantum physics or astrophysics or whatever, they pretty readily acknowledge that it wouldn't surprise them at all if, during their life there's like another major shift in physics where we realize that we were completely wrong about a lot of fundamental assumptions. That's not uncommon at all. It's kind of only in these like debate circles online that
What's his zzpop?
Yeah.
He's like an actual astronomer. I can't remember. He has credentials of some sort, right?
Yeah, he has a
So,
PhD in physics.
Yeah,
if I'm not mistaken.
cosmology. I am heading off
okay.
soon.
You're still
Yeah,
here. Excuse
but
me.
sorry, getting
I've
ready,
heard your
but
name
still
tossed around. I
overheard
just
that.
haven't ever
Yes,
talked with you. But
yes,
yeah,
I do
cool.
cosmology, teach physics.
Cool. You or Blitz put out more facts per capita.
Blitz? Is that?
Yeah, Blitz PhD. Oh, you don't know him?
yeah.
He's got a presence on YouTube and TikTok.
Yeah, cool. Yeah, I don't have any
And-
YouTube or anything, but it would be cool to make one someday.
Yeah, I was just curious. I thought you might know him.
That's
Yeah,
all
I
I know
mean,
is
that's about-
that dude got cooked when he was talking about creationism, man, and he had to dip out. He dipped out and left me with this other little buddy that was there, and then he just was so
did you
bad
talk to him
faith.
about creationism recently, or
Yeah, it's been
has it been a
probably
while?
some
I'll have to look back. Yeah,
I
I've seen
forgot
a
the
lot of
guy's
his
name,
stuff.
but he's like that real like cocky guy with the curly hair. You know what I'm talking about? He does streams with them a lot, and they'll be like, your God doesn't exist. Yeah.
He'll a lot of times he'll refer to him kind of midstream when he's like, "Oh, Unity." Is it Ian? Maybe like Ian, I can't remember the guy's last name, but I think
Yeah,
he refers to a guy named Ian a lot. That's one of his like people. It might be him or it might be someone else, but he's got a couple of other creators that he refers to often. I've seen some of his stuff lately, but he's been a little light on I guess on like more. He's been more focused on the creationism or like the debate of physicists. He was a little bit more into the flat Earth stuff until kind of recently. It seems like it's kind of thinned out a little. But every now and then he'll broach the topic. He'll get someone in there that wants to talk to him about stuff.
Yeah,
Have
but
you
I will
seen any
say,
of his
like, as
stuff?
soon as we start doing
Yeah.
like debates and stuff again, it'll just go right back to everyone talking about it, in my opinion, right? Like I think
Have you seen any of his like he's done a couple of lives and put out a couple of videos after the lives about muons and
and
there's
just
a
decay rates, which shows time dilation.
well muons they're not affected by like normal like refraction and stuff and they a lot of them form in the upper atmosphere, but they're a result of this what am I thinking about? I think I'm
They're
confusing
invoked
two
for time
things.
dilation.
There was an experiment that was done, or not an experiment, but there's a is it a muon detector that they had in somewhere like North Dakota or something like that, and they shot it across a few states, and the way that they had to angle the actual muon for lack of a better term, like I'm butchering it, but like
To account for the
muon
curvature.
generator. Right, and they shot it down through the earth, and the detector received it coming up from the earth. That's one of the lives that I think I've seen in the last 60 or 90 days. It was kind of interesting.
I've definitely never heard that. I mean, yeah, I mean, I look at it.
It is interesting. I mean, I was like, okay, what's this going to be? And he actually broke out the paint and was like, this is exactly how they did it. Like, and the guy is a very I won't say stereotypical, but it was a very like predictable way that it sort of ran the gamut, where he was like trying to challenge every facet of the thought of like a very basic, like Austin, you could understand sort of the basic concept. There may be a way around it, right? Like there may be some sort of rebuttal to it, but it was a very basic way he was describing it, and the guy was just absolutely dodging sort of every basic part of it. But yeah, I'll find it and I'll send it to you in DM. when I find it.
Yeah, I mean, I'll look at it because when I
It's
looked into the
interesting.
whole
It's
muon
interesting.
thing, like people invoke muons to prove time dilation, and then when you actually look into it, you find out that they just assume that there's a certain amount at a higher altitude that we actually can't fully verify, and they assume that they have a certain lifespan, and therefore this percentage of them have changed, but they shouldn't actually make it to us. So therefore, if we assume that they're only created at these altitudes, and then we receive some at the ground, then it must have actually experienced time dilation. It's like, wait, what? So I don't
Well, they
know
did.
about this.
Well, this is a different experiment. I might be actually crossing terms, but muons, they did an experiment in like, I want to say 1956 or somewhere thereabouts. I watched the entire thing a few weeks ago, actually. And it's a very particular way that they set up the experiment. And they went, you might be talking about sort of the same thing about the time dilation, where I think they were in Colorado, where they were up at altitude for the very first part of the experiment, and then they went down the mountain, and they were at the bottom of the mountain for the second part, and they were receiving about the same muons, but whatever the conclusion was, and I can't remember exactly what the latter part of the experiment was, where they were like, this is because of time dilation. I think that was
Oh, I mean, I
like you're
remember it. It's
saying
pretty simple.
muons. Yeah.
It's pretty simple. It's
Go
pretty
ahead.
simple. It's like that we know the lifespan of the muon. They claim they start at a certain altitude. So to get down to the surface, they would have to exist for however long it takes them to get there. But they should actually not exist by the time they get to Earth. So since we're detecting muons on the surface, the only way that those muons could have traveled that distance with the lifespan that they have is if they experience time dilation, right? So they haven't reached the climax of their lifespan by the time they get to the surface, that greater distance.
Right.
So it's like
Yep.
it's like this indirect inference of it. But the issue is when you look into like the assumption of the starting point of the muons. So it's
Okay.
like that. Well, like that's not really verified. It's a theoretical framework. Like they say that they believe that that's the conditions in our atmo, the closest to Earth, that's the most conducive with the production, large scale production of muons. If you grant that first assumption, and then you grant the consistency of the lifespan, then yeah, in theory, something like that would explain it. You know what I mean? But what's also interesting though is like kind of like what he was just explaining. Um, like what exactly is time? Because like a lot of people make the assumption that some type of physical length contraction or what we call being time dilation, which is really just a physical effect on whatever mechanism we're using to measure time, right? Like it's not like we can go grab some time or whatever. Like yeah, all of those, both those things can easily be affected with electric and magnetic forces, right? The main contention actually comes with the exactly sufficient amount needed to explain why we can never detect the motion of the earth. It would be somewhat complex, right? Like if the muon's moving down to the earth and you're going to invoke just like a strictly like a Maxwellian electric magnetic contraction, and then say that that corresponds to whatever device we're using for time. And this is like what I was telling him. There's no logical reason. This is why Lorentz threw it out. There's no logical reason to think that if there's a real physical interaction, that the time and that the length are going to directly correspond. But anyway, like if you were going to try to explain something like that from outside of a relativistic framework, then you would have to invoke the medium that they're in somehow changing, right? Like contracting. It's not in theory impossible or whatever, but like I just don't. The evidence isn't sufficient for me to need to actually provide an explanation, right? So the muon time dilation thing for me is tossed out. They never verified where they claim that they started, and then even the time span is also pretty sus. But if I've heard the claim about like neutrinos like being received from the sun through
That's what
the
I was talking
earth.
about.
Yeah.
Yeah.
So they come up to like our feet, wherever supposedly they're going through the earth from the
That's
sun.
the experiment. Yep. That's the experiment that
Yeah.
I'm talking about. Yep. And they're generated in the upper atmosphere, though. But they originate from the sun, most of them. But they are unaffected by. Oh wait, no. You're talking about muons, or no. You're not talking about muons. When I'm talking about the upper atmosphere, I'm talking about muons. Neutrinos, though, are byproducts of the sun's processes, and they are unaffected by refraction. And there are neutrino detectors and neutrino emitters, which is what I'm actually looking for the video right now as you've been speaking. And I knew it wasn't
Neutrinos
muons,
are
it's
highly
neutrinos, yeah.
sus, bro. Neutrinos are highly sus, bro. So like the whole entire interpretive framework is sus. What they claim that they are, how they claim that they detect them, and then when you actually look into like the major neutrino detections, it's largely software dependent. So it's like largely dependent because of like the noise. Yeah, I mean, just because and then I'll yield them to them on this, whatever. But at one point, based on their initial interpretation of what a neutrino supposedly, which is actually just like more so, it's a mathematical requirement, meaning like like the like Cherkanoff radiation, right? It's like we shouldn't have that much energy. There must be something else that's taking place that's causing more energy, and so then we get this when we're detecting things that don't fit within the standard particle physics model. We gave it a different name, which is basically there's more energy here, and it doesn't act in a way that we can really understand. It almost goes the speed of light. It doesn't seem to have any physical interaction with other things. It doesn't get intercepted with anything. Doesn't have any like material or corporeal component, right? It's like it's just this long story short, like an etheric framework explained neutrinos perfectly, and a non-etheric particle physics ones doesn't. You have to create neutrinos. Then they started saying like, wait, it looks like it's moving faster than the speed of light. That's in relation to the medium, meaning like in Cherkanoff radiation, like how quickly they see the neutrino, quote unquote, it moves faster than the speed of light in water. So it's not literally faster than C, but it moves faster than the speed of light in water, even though it's in water, which they don't even explain that. They just say, like, well, it's not actually C. It's like, okay, but how is it moving faster than the speed of light? So then they have this issue where like neutrinos are somehow magical and they can actually move faster than light can through water. I don't know. It's just like a whole thing. I mean, neutrinos are like, dude, I've talked to like 2 or 3 different people that like specialize in quantum who say it's very possible neutrinos don't actually exist.
Yeah,
My
Austin, I'd love to chat with actually
my
people who've done these measurements with the atomic clocks themselves as well.
my
Go ahead,
simple
Dicey.
contesting, yeah, excuse me, Eden. I would say how do they actually detect them if they don't exist? Because they have a neutrino detector. What are they detecting? Because they actually show it, and Blitz shows it in the video. I tagged you in. I also sent it to your DM. He shows the actual papers about how they are not shooting neutrinos, and then all of a sudden they start shooting neutrinos, and it spikes off the page, right? So they're
Okay, yeah,
receiving
they
it
don't detect the
from somewhere.
neutrinos though. They don't actually detect neutrinos, right? That the official stillman is that they're not detecting the neutrino. They don't like capture the little neutral like ghost particle called a neutrino. They measure the flashes of light or electrical charges produced when neutrinos collide or when they like hit a subatomic particle. So what they actually measure is like they don't see two particles that can be actually directly detected, but all of a sudden they see an interaction. And they're like, okay, that must have been a collision. Or they see these other subatomic
I can grant
particles.
you that, though. I can grant you that. What's the difference? They're detecting
There's no
something
direct
that they
detection of
emitted.
the particle. It's just assumed.
But there is a direct detection in the form of light, right? Like in a collision that you said, right?
What we're detecting is like a flash of light, yeah, or like an electrical output.
That's still a direct detection, regardless.
That's an
Like it's a
indirect
byproduct.
detection.
It's a
Well, no,
byproduct of whatever the collision was. That
byproduct
was
means indirect.
by.
So it's not a direct detection.
Okay, so if you want to split hairs, like what caused it,
What?
right?
Okay,
I'm
but wait,
just saying
time
if you
out.
want
It's
to.
not splitting hairs though, bro. It's like a fundamental difference, like a direct, like it's just
So
like
where'd the
how
light
we
come
don't.
from, though?
Time out.
The flash of light.
It's like basically what you're asking me is the same as if it's like, wait, no, we haven't directly detected dark matter. It's an indirect inference, and you're like, well, we see the effect of it. So how else does it happen then? Yeah, I could be completely retarded and not know how to explain it at all. It doesn't make what you
Can I
said
challenge you?
real.
Uh,
Yeah.
what I would challenge you to say is like, oh, we don't detect like direct sunlight during the day. It's scattered throughout the atmosphere. Like that's what you're saying right now.
No, we can easily detect sunlight.
Okay, then how do we see the blue sky? That's a byproduct of the sun, right?
But we have optical. You realize that
But
we
we
have
detect it.
electro-optical imaging that we can detect the full spectrum of sunlight.
Sure, but we can detect the sunlight because the sky's blue. Like we know that the sun's out. So like, why can't
Okay.
we detect? Can't we detect a flash of light as a result of something that was emitting light in
Well, I
that
don't think
direction?
no one disagrees that it's the effect of something, right? Like what's challenged is this magical particle that borderline defies physics that no one can explain. They claim doesn't have a charge, although it still has elementary charges and can penetrate matter. It only shows an effective collision with itself and rare subatomic particles. It can go faster than the speed of light in water. It typically goes just about the speed of light, and it literally just goes right through matter. That's like an insane claim. So that's like a admittedly in 2026 at the top level of physics and quantum physics, they admit the neutrino is insanely confounded and we don't understand exactly how it works. So like that's like a huge thing to grant. It's very similar to dark matter. We don't know how it works. We don't know
Yep.
what it is. We can't observe it, but it must be there because if it's not there, I don't have another explanation. It has to be there because my equations don't work. But my explanation is very simple. Your equations are stupid and you're assuming everything is a material, corporeal entity like little physical particles, but they're not. There's a permeating background. The background permeates all of space. All of these phenomena are excitations within that background. So of course you might get a flash of light. There's no such thing as virtual particles either, right? It's just an excitation of the background. That easily explains it. Sure, you would have to take the next step, and then you would have to identify the different excitations and phenomena, and like you should name them probably so that we can easily replicate the phenomena and isolate them or whatever. But the leap is where it's like it must be a particle, and the neutrinos, quote unquote, everything that's attributed to neutrinos shows us every conceivable characteristic that isn't consistent with any type of physical particle. But they have to call it a physical particle because that's their whole model. Physical particles don't go through matter. You know what does that even mean?
Unless someone wants to claim that right now. I see Spin. Do you want to claim that?
The physical particles don't go through matter.
Yeah.
Do you consider neutrinos physical particles because
Well,
they go
that's
through
what they
matter?
claim. That's my whole point.
Yeah.
They claim that they're the only
Well-
physical particle that go right through matter with no resistance.
That's fine. So what is your evidence to back your claim that that doesn't take place?
That's not how that
Because
works.
it's not
First of all,
possible.
first of all, that's
Well,
not how it works. But
no, that's how the burden of proof absolutely works.
that's
You said
that's
physical
shifting the burden.
particles don't go through. Wait a second. You made a
Can I say
claim
something?
that physical
Sorry, can I say
particles
something?
can't go through matter. Yeah, hold on a second. You made a claim, Witsit, that physical particles can't go through matter, right? That's a positive claim. The person that
Okay.
has the positive claim has the burden of proof. Like,
Okay, so look, here's the deal. You're making a positive claim that something called a neutrino exists and that's a physical particle with mass
and
and
it's
it goes
detectable.
right through matter. And no, it's not detectable. It's not detectable. It's objectively not detectable. You guys claim that it's not directly detectable, right? You assume it exists
I
because of an
mean, your
indirect
boy Eden up
observation.
here actually posted from Blitz to show that it is detectable. If you want to look at the chart, I mean,
It's factually
taking
not
it-
detectable. I don't have to look at a chart because I know the official explanation is that we're not actually detecting the neutrino itself. What we're detecting is the flash of neutrino collisions or neutrinos colliding with a different subatomic particle, and you either get a flash of light or an electrical discharge. We are quantifying that with the input of
As
the
it
neutrino.
collides with a particle. Yeah, as it interacts with a particle, which it does rarely, you get a flash of light. Thank you.
Oh,
So
wait, I thought it went through matter.
most of the time.
Oh, so sometimes it's sentient.
No, it's not sentient.
It's
It's
getting
just
more
it's
interesting.
very small.
So it
And
I
so
say
there's a lot
something?
of space. There's a lot of space for it not to hit.
Oh,
Can,
okay. So it doesn't go through matter. It doesn't actually go through something. It doesn't go through mass itself or something corporeal. It's actually dodging
No
every
defined mass
constituent
though.
part of mass. Is that what you're saying? Like if it goes through a door, it didn't actually go
Well,
through
you
the
know that, like,
matter of the door. It just shucked and jived and
you,
dodged
you
all
know,
of the matter in the door, and
that's
that's
how
why it
they.
went through it.
That's how they discovered. You know, protons, neutrons,
can I have a
neutrons.
say?
When they shot it at gold, and every once in a while
Yes.
one bounced back, but most of them went through. Yeah, this one's just smaller and interacts less. It's the same concept.
Okay,
Can
thank you
I
guys.
have a say?
Yeah, go
Sorry.
ahead, Franco.
Can I have a say?
Yes.
Okay, since I'm not sure who else is a sort of involved in this professionally, but I am. But as somebody, someone of you know, I'm a particle physicist myself, so an experimental one. So I have some corrections to make to what Witsit said. It's not. It's not. It's true that a neutrino is detected when it interacts, but this is true of any other particle. It's only detected through interaction with an instrument and interaction with the rest of matter. And the other thing is that it's not correct. It's not that it's true that the neutrino goes faster than light in water, but what he was, I think he was referring to is the fact that in detectors such as Super Kamiokande, the water-based neutrino detectors, what they detect is Cherenkov light that is produced not by the neutrino, but by the electron that's emitted when neutrino interacts, and that electron goes faster than light in water. It's the electron that goes faster than water, the faster than light in water, not the neutrino. And this happens with lots of other particles. It's the principle of Cherenkov detectors, which are used in, for instance, in some of the LHC experiments, such as LHCb. They use normally we use Cherenkov light detectors that are based on the fact that relativistic particles, when they traverse a medium, um, they emit a sort of shock wave due to the fact that they do move faster than light in that medium. And so they produce a sort of sonic boom cone of light, which is called Cherenkov light. And that is actually a way of measuring the velocity of a particle and thereby identifying it. Because if you measure a momentum of a particle, of a charged particle, through its deflection in a magnetic field, and you measure its velocity using a Cherenkov detector, then you can derive its mass, and then thereby identifying the particle. That's commonly used in particle physics, and it's not just the neutrinos. It's any relativistic particles and it needs to be charged, so not a neutrino, in order to be detected by Cherenkov detectors. And okay, so neutrinos were thought to be massless until oscillations were discovered. So when I studied the standard model of particle physics, when I graduated almost 40 years ago, then it was taught that neutrinos were exactly massless. In the standard model of particle physics, they are exactly massless. And so they move at the speed of light. They were thought to be moving at exactly the speed of light. But then in the recent decades, it was discovered that neutrino undergo the phenomenon called oscillation, flavor oscillation. So they oscillate between different identities, different flavors. And in order for that to happen, they need to have a mass, even if it's very, very small. So we don't have a measurement at the moment of the mass of neutrinos, but we have some upper limits. But it surely is not exactly zero. It's certainly very, very, very small.
because the speed is been measured to be even from supernova data, and there are a lot of other data that confirm that the neutrinos do move at the speed which is experimentally indistinguishable from the speed of light at this
Okay,
level
Franco.
of precision. Yes.
Thank you so much for your time. Have you actually? Well, welcome to the conversation. Have you? It seems like it's been a while. Have you ever measured or observed anyone, or maybe gone to the lab to observe these neutrino detections? And thank you.
Well, there are plenty of neutrino detectors. One actually reported. I saw yesterday. I didn't read the paper or the press release, but there was an announcement by the Ice Cube collaboration. Ice Cube is a neutrino detector which is in Antarctica, and they allegedly detected a very high neutrino with an extremely high energy coming from outer space.
What
And
is it
so
called?
Ice Cube,
Oh, yeah.
Ice Cube, like the ice cube you put in your Coke.
I did hear
Uh,
about that as well, about in Antarctica. Austin, do you have any thoughts? And thank you,
so
Franco, as well.
I didn't read that, but I only saw saw it on Twitter. I think I saw the announcement and with a picture, but I didn't have the time to read it because I'm busy these days and with exams. Actually, I have to go in a while because I have I'm very busy with some exams.
Amazing.
But as far as neutrinos being detected, I personally knew Jack Steinberger, who got the Nobel Prize in 1988. Actually, I always I always tell this to my students that he actually bought me a pizza here in Pisa uh, 1 week before
That's
1 week before
that's cool.
getting 1 week before getting the Nobel Prize, and so because I was the only.
Oh, wow.
Okay, that's an anecdote. I was the only one. Me and a colleague of mine, we were listening to a lecture of his, and then they offered us a pizza, and then my colleague said, "No, I have something to go, somewhere to go." So it was just me and him, and 1 week later, he got a Nobel Prize. So my friends say, "Oh, you brought bad, good luck to him." But okay, that's simply a very stupid anecdote. But this guy, he was the head of the experiment I was working at in the moment at that moment, which was called the Aleph experiment at the lab at the collider, and he got the prize. The prize he got it in 1988, but the experiment he got it for was done in 1964, I think. So 22 or 24 years before, and that was the experiment that actually showed that the muon neutrino is different from the electron neutrino. So he made a muon neutrino detector experiment, and he established without reasonable doubts, and indeed such that he got a Nobel Prize, that the muon neutrinos are different, a different species, different flavor than electron neutrinos. So yeah,
How many
we can
flavors?
detect them, and we do
Yeah.
detect them.
But well, do you? Like, so this is like, just to kind of run this through like a skeptical perspective, right? Like, so for years and years and years, the standard model of particle physics stated that neutrinos were massless. But
Yes,
then after years of not being able to actually detect them, and it matched like the amount of neutrinos that were supposed to come from the sun, so like the solar neutrino problem, they eventually introduced like flavor oscillations.
yes,
So it's this idea that the neutrino has multiple flavors. I thought it was like 3, but I don't know. And it's basically
yes.
like a
Three.
superposition of all 3 flavors that it oscillates in between, the 3?
Yeah, it it can oscillate between these three, and of course, yes, the flavors, the three neutrino flavors were in the model well before oscillation was discovered. So they were thought to be governed by lepton flavor conservation. So what they could not oscillate between them. So a mu neutrino was a mu neutrino. It could never change to an electron neutrino. That was the tenet at the time, and that was exactly what the Steinberger got the prize for. He detected mu neutrino and mu neutrinos and established that they were different than electron neutrinos, meaning a mu neutrino, when it interacts, produces a muon, an electron neutrino, when it interacts, it produces an electron, and that they always does this. But then it was found that they can oscillate into one another, and this was triggered by the by the solar neutrino deficit, and of course at the time when it was discovered, since people were blaming the solar standard model, meaning that the model predicting by how many neutrinos were coming from the sun, were predicted to be coming from the sun, was wrong, because it was based on that prediction. Of course, the fact that you saw fewer neutrinos, than you expected, and so people said obviously the model is wrong. But then there were now there's plenty of different kind of experiments that prove that neutrinos actually oscillate, flavor oscillate, and this is by the way, flavor oscillation is something that you see is a very typically quantum behavior that you could see in, for instance, in neutron mesons. It was discovered first. It was discovered in neutral K mesons, but now we observe it in neutral B mesons and other kind of neutral chargeless particles, and it was observed in neutrinos, and that's why long baseline, so-called long baseline neutrino experiments, such as the CERN to Gran Sasso, and that was active in the 10 years ago, or no, even 15 years ago, let's say, and then now the Dune neutrino experiment that is being designed and built, that will send a beam of neutrinos from East Coast to West Coast in the US, and that's precisely to measure oscillation.
Okay. So just to clarify, right? Like, they expected to get a bunch of neutrinos from the sun, but they weren't getting it. They don't claim to like even know the mass of them, right? So like they claim to just measure the difference in the masses of the flavors. Is that right?
They measured the amount of the number of neutrinos as a function of distance from the source, and that exhibits an oscillating behavior, meaning that it's oscillating as a function of distance, and the meaning that along the way they they change their flavor, and so when they're detected, this is the kind of behavior that one sees, and for instance in neutral mesons, and so as a function of the distance traveled and of the neutrino energy, you can find that there's a probability that it will be detected as a neutrino of one flavor or another flavor. This is the oscillation thing, and this behavior also depends on the mass of a particle, meaning the theoretical explanation of why this happens. So
Gotcha.
they
Yeah.
need to have a mass, but you're not measuring you're not measuring the mass directly. You're measuring this oscillation behavior, and this is linked to the mass.
We're not actually measuring anything directly, right? I mean, we're measuring the interaction. You're saying that
Yeah,
we
but
all
this
see that,
is,
but yeah, but
as I
yes,
was
I mean
saying, this is
that's
also true for an
standard.
electron, and
Yeah.
for a photon. For anything, you only measure it when it interacts with an instrument. So
Yeah. Yeah, definitely
Yeah.
for photons. I mean, electrons are a little interesting, right? Like when we look at really what electrons were just at the time the smallest quantifiable charge. And so we just called it an electron, and now we say that you can never actually isolate it or find it, and it's just a probability distribution, blah blah. You see that like all these things make more sense within the etheric framework though. Because
Sorry.
there's a fundamental primary background, and all these are different variances of excitations within that. I don't really need to believe in like individual constituent particles bouncing around that have different variations or whatever. But like, I just want to make sure I do understand this though. Like, they thought they were massless, and now we kind of infer that they have a mass based on the different ways we're able to detect the interactions. Is that right?
Yeah, we now infer that they must have a mass, otherwise they wouldn't oscillate.
Right.
And
Okay.
yeah, but the mass is very, very tiny, and we don't have a measurement of the mass as yet. We have upper limits on mass differences and things like this. But they're very, very tiny. They're really, really. I don't have numbers right here, but I can
That's all
look
good.
them up.
Yeah, it's all good. So, because then this whole idea of them just kind of going through matter would be because they're so tiny and so close to massless, although technically not massless because they can't be because they oscillate, that they're able to penetrate matter oftentimes because they basically avoid any other mass that they would collide with.
No, it's not. It's not a problem of mass because, for instance, muons can do the same thing, much the same thing as well. We are being penetrated, so to speak. We're being traversed by muons, by hundreds of muons a second, all the time. You can detect them. We have, for instance, at the LXG experiments, which are hundreds of meters, 100 meters. My experiment CMS, and the previous one was at LEP was Aleph was 150 meters underground. So there's 150 meters of rock above it, and we could see lots of muons coming from the sky that they just go through 150 meters of rock. Muons are the particles, the charged particles, and their mass is not negligible. It's the same mass as a mass of a pion, as a pi meson. They're more than 1/10 of the mass of a proton. Certainly much much heavier than an electron. A muon is much heavier than an electron, as well, about I think it's about 200 times heavier than an electron, and this is, but this is not the reason why they don't interact. They interact very, very weakly because they only interact electromagnetically. But since they have masses higher, for instance, a muon interacts much less with matter than an electron because it's heavier, not because its mass is small, but because it's high. So it's sort of not stopped by the fact that it's interacting electromagnetically
Oh, it
with
has more
matter.
moment. Has
It
more
has more momentum. Yeah.
Gotcha.
And so it's not stopped, and it only interacts electromagnetically. A neutrino does not have a charge, so it doesn't not even interact electromagnetically. It only interacts with a weak force, and so that's the reason. The point is that the probability of interaction is very, very, very low. So it doesn't got to do with the mass. It's got to do with the sort of the charge. So it's not charged, and the only way it can interact with the rest of matter is through weak interactions, and they're called weak for a reason. The probability is very very low, and indeed, for instance, in the standard model, only one type of neutrinos, so-called left-handed neutrinos, are present, because the so-called right-handed neutrinos, either they don't exist, or if you want to include them in the model because of symmetry, say if there exists, if left-handed neutrinos exist, the right-handed should exist, but they're not interacting with anything. So that's one kind of thing that you say, they exist, but they don't interact with anything. So it's the same as they don't exist, because if something exists mathematically, but it doesn't interact with anything, there's no way of with no interaction that's known, that then you may as well say that they don't exist. And this is for the right-handed neutrinos. The left-handed are the only particles that only interact weakly with the rest of matter. That's why they penetrate. So
you can see, okay, that's very interesting. So you can see though, someone would say like a particle that like changes its identity when no one's looking and whose exact like physical mass can't be measured, and it seems more like a mathematical ghost particle that's just patching up equations because they're mathematically predicted. And it's kind of just, we see an interaction, so we know something must be causing that interaction. And so to me, what it sounds like is it's like something super hard to detect, but all of a sudden we have these particles, right? We have an electron or a muon that people are calling it or whatever. So then we assume it must be from like this semi undetectable, or really just undetectable particle we call a neutrino that doesn't have a charge, because we're not even detecting a charge. So then it's like, oh, well, now it has different variations because we're seeing this same phenomena happen with multiple other particles, which is like there's nothing seemingly there to cause the interaction, but all of a sudden we see an electron, right? Like, so there's,
And th-
so my problem
think,
is that if tomorrow you guys see it happen with another particle, you'll just claim there's a fourth type of neutrino.
and Austin, if I may add, if you don't mind, Franco, as well, I think these detectors are only a mile below the surface. Am I incorrect?
which detectors? I don't know. There's plenty of neutrino detectors in the world, so I don't know what
Okay.
detectors are you referring to?
Well, I'm looking at one from Japan and one from the United States, and the one in the United States is approximately 1 mile, well, less than that, if I'm not mistaken. And then the one in Japan is 0.6 miles. So I see
Underground?
that, yeah, underground, yeah. So the claim is that they're shooting through the surface of the Earth, and then they're detecting them about a mile underneath the surface. And think,
No.
Well, claim it comes up
One
out of
one
there.
mile 1 mile underground. I've never heard,
okay,
but I've not. But okay, no, they're shooting it. They're shooting the neutrino beam. Say to other parts of the world, to another point of the world, because they need to have a very long, these so-called long baseline experiments. The path that neutrino has to follow is very long. It has to be long in order for oscillation to happen. And so that's why, for instance, they did it from CERN to Gran Sasso, which was 7,000 kilometers, and then they are now planning to do it from East Coast to West Coast in the US, which is a lot more than that. And so they're going through the crust. So and of course, in order to do that, they have to be directed not horizontally, but at an angle, and to take into account Earth's curvature. I'm sorry, guys, but and then but this is you have to traverse a lot of Earth's thickness of crust, but because they move almost horizontally through the crust. As for the other thing, it's not that it's something that we don't know, and we think it's undetectable, so we call it neutrino and so on. No, it was not like that. It was the way it was sort of postulated in the first place, because it was historically neutrino was it was postulated because there were some radioactive decays, the beta decays, where an electron is emitted, such as I don't remember, but there's you can look up any beta decay. Potassium is some bananas emit positrons, but there's a in one particular beta decay that we're studying, it appeared that energy and momentum were not conserved. You had particles going, the products, the beta decay, there's for instance a neutron that converts to a proton and an electron. So a neutral particle, a neutron in a atomic nucleus, becomes an electron and a proton. So the charges and the masses add up more or less. And but the momentum, the total momentum and total energy apparently were not conserved. And so people were really puzzled by this, and some theorists even thought that maybe, after all, momentum conservation, energy conservation were not universally true, but this was would have been a real shock. But then Pauli, I think, thought maybe there's another explanation, maybe there's something else that escapes and takes away the missing momentum and missing energy, and we call it. He thought the first. I think he called it neutron because it wasn't. The neutron was not named as such as that like that at the moment at the time. So it was the first. Proposed name was neutron, and then Fermi came along and proposed to call it neutrino because the ino suffix is Italian, meaning small. So because neutrone was a neutron, it means big one, and neutrino is small. So that's the origin of this book, because the Fermi was Italian. But then that was the way it was proposed as an explanation to explain to recover energy and momentum conservation in beta decays. But that was long ago, and then they were actually detected, and we found out many things about neutrinos, the spin and so on, but the left-handedness and so on. But about what Witsit said, maybe you will discover a fourth type of neutrinos. People were actually looking for those. We were, and one of the greatest achievement of the LEP experiments, particularly Aleph, the one I was working, the experiment I was working with LEP. Aleph actually, and the LEP experiments actually determined, by looking at the decays of the Z boson, that the numbers of neutrinos with light with a very low mass, and indeed a mass that's really negligible compared to the Z, is 3. It's actually 3. We measured the number of neutrino families to be 3. And
Okay, thank you, Franco. I have a question, if that's okay, afterwards. So,
yeah.
just for the room, if that's okay, from my understanding, there were these two observations in the US and then Japan. So, as they traveled through the surface of the Earth, it was detected, I think they said trillions of neutrinos were sent, but 50 to 100 were probably detected a millisecond. And then in the United States, it was 4.3 milliseconds after the transmission. Do you think that's accurate?
No, I would have to look at the numbers but you said what you're asking me if it's accurate is the timing or the number of detectors or
Precisely the timing. Yeah. I'm not. Don't worry about the details. I don't want to hold anyone to. Yeah, because if I haven't read something either, I wouldn't know. But yeah, I was just thinking. Do you think that would be accurate? So let's say if we send the neutrinos from the lab, and then we're at the detection site, just waiting. We power it on. We're waiting for detection, and I think it says for Japan, traveling the 295 kilometers through the surface, it only took 1 millisecond from what I'm seeing here. And then in the United States, 800 miles took 4.3 milliseconds.
Yeah, it's the speed of light. Yeah. It's consistent, I think. Yeah.
Okay, thank you. And I'll send you.
Just make sure everyone actually knows what's going on. When they claim that they shoot neutrinos, right? I mean, people just hear that and they think they like pull out a ray gun that's full of neutrinos or something, but like no, they're just using uh electromagnetic waves, right? Like high frequency electromagnetic waves. And they have like superconducting radio frequencies. So they claim that they like there are different ways they claim they do it or whatever, but they like say strip certain particles of like protons or whatever, and then when they get their certain types of particles they want to send, they introduce like high frequency electromagnetic waves, and then these protons surf on these electrical fields that make them go practically the speed of light, right? And then like they use magnets to like compress them into a super tight dense like pulse, and so they're when they use these high frequency electromagnetic waves and these magnets to basically condense everything into like a dense pulse outside of this like neutrino gun, whatever you want to call it, right? That's how it's
Yeah.
like portrayed. And then they claim to detect it at however far away. And they claim to get a fraction of them. But what is known, and almost no one talks about, but it's well known, one of the biggest difficulty with supposedly detecting these neutrinos is background noise.
Yeah.
It's so difficult to actually isolate this supposed neutrino from over there with the immensity of background noise.
Yeah, that's why they need to be shielded. And yeah, the background is a problem with any measurement. It's a problem of experimental physics. One of the problems is getting rid of the background or estimating it, its contribution, and so on. That's not just with neutrinos. It's with it was there with the Higgs boson. With any other signal, you have a signal and a background. You have to learn how to distinguish them and to how to measure what the signal's significance is, and so on. By the way, so a couple of comments, then I think I'll have to leave because I need to go and do my job. But one thing, well, what Witsit described is the way you produce something like proton packets in bunches in an accelerator such as LHC, but the way neutrino beams are produced is well, does not need to have compressed protons and things like that. What you need of course, you start with protons because they are easier to produce, and then you hit this proton beam onto a target, and then what comes out of this kind of hadronic interactions of protons with matter is a lot of other particles. The vast majority of which are so-called pions, which is pi mesons. Pi mesons, which are can be charged or neutral. Neutral pi mesons decay to 2 photons immediately, and pi mesons actually decay to 1 muon and 1 neutrino. And then the muon is charged, and then you can deflect it away with magnetic field. And what remains is a neutrino beam. And of course,
Okay.
it will not have a very definite energy, but you can sort of select energies by basically knowing the pion energy and knowing the muon energy. Then you can deduce what the neutrino energy was. And so
Yo, I
there's
like
a
this
way of.
Franco guy. Yo, I like you, bro. So okay,
Thank
real
you.
fast, cause yeah, man. So like my understanding is like the way that they do this with the neutrinos is they use like GPS synchronization. Because like if they're going like the speed of light, like even if you're far away, right? Like you're gonna shoot a beam of neutrinos supposedly, and then it's gonna be like microseconds by the time it gets somewhere. And then what they do is they know how long it should take. So they do like a pulse of beams, right? And then they know how long it should take to get to them. And then based on the amount of microseconds it should be, they open up like a little timing gate for that window, right? And then that's how they're supposedly receiving and then sifting through what they received. So there's just an assumption there that that's actually what they're receiving, right? Because like in theory, if you didn't open up the timing gate right then, if you picked another time, you could still sift through and find neutrinos or whatever. So, and I'm not going to claim to
Yeah.
know more of the specifics of this, where it's like, no, for sure they've tried that, and then they've tried the timing gate with the beam, and they found out that they got way more neutrinos with the beam. I'm sure someone may claim that, but I'm open to seeing if that's actually been done. But I know that what they do is they synchronize the test. They open the little timing gate based on when it should arrive. They assume that they're receiving that beam, and then I'm deferring to Franco here, which it was very interesting, like because it makes sense what they're saying, right? If within their model they know
Yeah.
that it breaks down to specific things, the muons have a charge, they can deflect that away with the magnetic field, so they know that all the muons that are breaking down in the decay, they're getting those out of the way, right? And then you're basically going to get it to where you're isolating the only thing that could be there is going to be a neutrino.
Well,
Like,
I'm not sure about the details of how they synchronize this, but of course, if you use GPS or not, but of course, you've probably heard of the because I mentioned this many times earlier previously even in this kind of spaces, the infamous opera result. Opera was this Gran Sasso detector in Italy, and supposed to detect neutrinos sent from CERN, and they in 2012 they came out with this incredible announcement that have measured the neutrino speed to be faster, even though by a very tiny amount, faster than the speed of light, and
oh, but they
and
came out and
and
fixed that, right?
and then they discovered that there was basically a malfunctioning cable that was the origin of that, was introducing a delay that was not taken into account in computing the velocity, but this is a very sad story, because it basically was due to the fact that some physicists wanted to claim for themselves the glory of having made this shattering discovery, and so they leaked it out to the
What?
press. They leaked it out to the press too early before the necessary checks were made, and so they were forced to release this to the press, and then they were basically debunked, and that was very
Humiliated.
very sad. So I don't know the details, but surely the purpose is not measuring the velocity. It's not measuring the speed. It's measuring the amount of neutrinos you get, and the knowing about how many you started from, and especially in the so-called appearance neutrinos, appearance experiments, is that you send, for instance, if you produce neutrinos the way I described earlier, meaning from the decay of pions, then they are muon neutrinos. And so you produce only muon neutrinos. If you detect, for instance, tau neutrinos, which were not produced, then it means that these tau neutrinos were produced along the way, and so it means that the muon neutrino turned to a tau neutrino before being detected, and if you detect instead an electron neutrino, that is controversial. That you might there's a background to this observation, because when you produce muon neutrinos the way I said, you also have a contamination by electron neutrinos, because the muon themselves, after a while, they decay to electrons plus a couple of neutrinos, one muon and one electron neutrinos. Actually, they decay to one muon neutrino and one electron antineutrino. So if you and an electron. So if you detect an electron antineutrino, it means that it actually comes from the decay of the muon. It's not an oscillation of a neutrino, of a muon neutrino. one other comment I wanted to make before I leave. Sorry if it's not exactly related to this. It was about what Witsit was saying earlier. The way we measure, I even posted half an hour ago a picture to the chat. The way we measure time dilation with muons is not just with the atmospheric muons being detected on the surface. It's there's this very famous so-called wiggle plot that's measured at the G-2 experiment in the United States that shows a muon decay spectrum, so to say, curve. Actually, this is meant to be measuring the oscillations due to the G-2 effect and the precession in a magnetic field. But the envelope of this wiggling curve is an exponential. You can see that it's exponential because it's in logarithmic scale. It's a perfectly linear plot, and you can that spans something like 6 orders of magnitude. That's really impressive, that plot, and you can fit it by eye by measuring the slope of that curve, of that straight line in logarithmic scales, meaning that gives you exactly the exponential factor, and so you can measure the lifetime of these muons in the lab, and these muons, you know, the energy of those muons, and it actually is exactly what is predicted by time dilation, and it's that this is the most recent plot, but it was done 30 years ago with the first G-2 experiments. We do, and we have lots of other examples of any time we measure, and we actually use time dilation to measure lifetimes of particles. We do use that. One of the experiments at LHC is called LHCb, measures only forward produced particles in collisions, because the forward produced particles, meaning at low angle in collisions of protons, are produced with a so-called boost. They have a horizontal component of their momentum, which is high, and that increases their lifetime. And so they, even if they're very short lived, by the Lorentz boost, they get to live longer, and so you can actually detect their decay. You can see there that the decay in a point which is separated physically, spatially separated from the point where they were produced, and that is only due to the fact that they have a so-called Lorentz boost. So we use this kind of things and special relativity every single day in every single calculation. So it's not just the atmospheric muons.
Okay, yeah, but like obviously like Lorentz contraction, right? I mean, it was originally proposed within an etheric framework, and like there's no experimental difference. Like there's no even an experimental difference with um so Henri Poincaré creates the 4D of time, and then it's developed into a 4D space geometry theory, which are both etheric and are experimentally identical to relativistic predictions.
But
And so, I mean, like,
okay.
I don't dispute that a physical phenomenon like this can happen. The only way that it could happen if it's real, actual, and physical, and has a mechanism that causes it. Relativity doesn't even offer a physical mechanism that causes it, but Lorentz's etheric interpretation invoked like a real physical mechanism, because we know, obviously, like we were discussing earlier, that moving, um, like the velocity of movement in terms of the magnetic or electrical component of any material composition, or say in this situation, quote unquote, particles, can
Okay.
actually contract the size.
Okay. The answer I decided a few days ago that that I would always use just this kind of objections. Not just this, but to a sort of class of objections. A quote from Feynman from one of his letters to a guy who was a relativity denier, and there's an exchange that I always post as an example how he reacted in 1961. Actually, this kind of people, and there's a quote that he said where he says I'm quoting by memory, so I might be wrong, but it says the only purpose of scientific thought is to predict what will be observed in given experimental circumstances. All the philosophical thoughts are an evasion to the point. So we need to have something that predicts what will happen in given experimental circumstances. Is that what I care about? I don't care if we have a theory and a paradigm which predicts, which describes exactly what we observe, and is capable of predicting what we will observe when we change the conditions, then fine. I'm fine with that. I don't care about the philosophy and how we interpret it, so if we have two theories that predict exactly the same thing, I don't care. To me, they are the same theory.
Okay, yeah, pragmatically, they're the same.
Yeah, they are the
But like,
same
but we're trying
physically.
to figure out what's
From
truly going on, though, bro.
the
We
rest
don't want to.
is philosophy. It's ontology. I don't care.
Well, but
Physics is
that's
not philosophy.
science.
No,
That's no science explains how things work. Like we don't just mathematically predict things.
no. Science. I just quote Feynman again. The purpose of scientific thought
Feynman's
is this.
retarded, bro.
Okay.
Respectfully, I don't think Feynman is like some authority I have to defer to. You know, like I think it wasn't actually retarded or whatever, but like, I mean, yeah. Well, I'll invoke Feynman
He
here and
was
say virtual
he was the
particles don't
first one.
actually exist.
He
Virtual
was the
particles don't
first.
actually exist, and they're just
He was
merely
the
a
first
conception.
person he was the first person that was fighting the authoritative principle. So, but his quote is something I completely agree with, and this is
So, like, hey, do you agree with this quote? Do you agree with the other
I'm
quote?
nobody as well, but I agree totally with his view of what physics is and what its
Gotcha. But do
purpose
you
is.
agree with his other quote where he's like, for example, like virtual photons have never been the input or output of
I
any
know.
experiment? Okay, but that's
We've
my point.
discussed this.
It's related to this same point though, which is he's making the
No,
point in that quote. He's making the point in that quote that it's mathematically useful, it's pragmatically useful, right? But it doesn't actually mean it exists. It doesn't give us any like viable explanation as to what's actually going on. It's merely abandoned to help us mathematically predict things so we can keep going. There's a difference between that and what's actually going on. That's the only reason I brought up that the actual Laurent, like, yeah, I get what you're saying for pragmatic purposes. If we have a framework that's able to show us what's happening, we can apply different standards and predict what's happening and it's accurate. That's what we need. That's all we care about. But that's not all that physics is because if like you're saying it's philosophical, but on the one hand, Einstein, the relativistic contraction doesn't even have a mechanism. So it's like, yeah, of course the math matches. He stole it from another person, right? He took the math from Lorentz. Of course the math works. Lorentz made the math up, right? And it's based on Maxwell's equations. But like what the relativistic application of it doesn't even make sense. There's no mechanism for it. That's all I'm saying. So like what I'm saying is everything that you're discussing, it works better within an etheric framework, and that's putting it charitably.
no. To me, and not only to me, if two theories have predict the same things, describe the observations and make the same predictions. To me, they're the same theory. I don't care about philosophy. I don't care about ontology. I don't care about what you call mechanism. What I care about is the description of nature, the description that works. That's what physics is to me and to
Let me
most
ask you another
physicists.
question. So say, okay, yeah, I get what you're saying. So we have two different versions of Lorentz contraction, whatever. They're going to make the same prediction mathematically. They're indistinguishable in terms of prediction. They're different in terms of like causal, what you're calling philosophical explanation. Okay. But yeah, it's only if we cherry pick the Lorentz. But if we take the relativistic application of the Lorentz factor, right? And then we just expand that out to the rest of the relativistic claims. It actually is at odds with quantum. It doesn't work. It's at odds all over the place with quantum. So like if you're gonna apply your own standard that like I don't really care as long as it works, well it's like okay then you would go with an etheric framework then, right? Because you still have the predictive advantage of the Lorentz factor with an etheric application, but now it actually isn't at odds with all the other quantum phenomena that relativity is at odds with. So if anything, you should throw relativity out, right?
No, I don't. I've not followed. Sorry. The current. I'm not a theorist, but current quantum field theory is formulated in a relativistic covariant way. So it starts from special relativity.
Yeah, but,
It's
what
at the
about
core.
general?
It's at the core.
But what about general
General relativity is
relativity?
something else. General relativity is something else.
Oh, I mean,
We're not talking about general
yeah,
relativity here. We're talking about special. I'm talking about
y-
special. I'm
I get
talking.
that.
Okay.
Yeah, special relativity works in quantum, but general doesn't, right? So
Yeah.
that was kind of my point though. Like general is just an expansion of special and it applies anywhere mass is. So it's like it doesn't work. But like an etheric framework would work. So this is the only point I'm trying to make to you is like everything you get out of special relativity is not exclusive to special relativity. None of it is. What is it? I mean, it's built off Maxwell's equations. Like none of it is exclusive at all, right? I mean, C, well, that's like a measured constant. We don't need Einstein for C, right? What do we need? Like, what's exclusive to special relativity that didn't already exist via Maxwell's equations, like the etheric Lorentz application? Like, none of it. Really, all I did was take it all and bundle it up, say C was absolute, throw out an ether, and then took his steps into general relativity, ultimately having to concede a dynamic equivalence anyway. But because I think the part that I get so confused by is like, why are quantum physicists not jumping at the opportunity to have a more viable framework? Like, if we have to invoke the Higgs boson field, there's basically a background that permeates all of space and it has overlapping endless amounts of quantum fields, and that really what we call particles are kind of conceptual. They're localized excitations within these fields, and this we have quantum foam and we have like vacuum energy and zero point energy and the Casimir effect and all these things, right? That show like the impedance of free space, right? Where there's clearly something that permeates all of space, and then we have excitations that come from within that. Why would we not implement the obviously more viable framework? Like virtual photons are no longer a problem if you have a actual background. They're not coming from nowhere. They're not popping in and out of existence, right? They're just a excitation of the background. I don't know. I've just never understood it. I don't understand why people are so dead set on holding on to the old paradigm. Like what's the benefit?
Great question.
What's the benefit in quantum to throw ether out? I genuinely don't understand.
Because it's not needed. I wouldn't know what to say. I'm sorry, but what we use now is very, very, very successful. You look at the quantum field theory. You look at the G-2 of the electron. Is something that is very, it's always quoted, but it's something that is really unbelievable as a level of precision and a level of coincidence between the theoretical predictions, and the experimental value at a level that was totally unprecedented in the history of mankind. At the
You're
level,
talking about the magnetic prediction.
the G-2 of the electron.
Can you
Yeah,
say it again? G minus. Is that what you're
2.
saying? Okay, G-2 of the electron.
Yeah.
In the quantum field theory?
Yes.
Okay, because
Okay.
if I'm not, oh, go ahead, Austin. If you were going to say something.
Yeah, well, see, okay, so as a precise measure of how the electron's internal magnetism deviates from the basic value predicted by their, yeah, because basically when you input the virtual photon, the math works, and then it's like the most highly precise prediction in physics ever once we accounted for the mathematical discrepancies of the standard particle physics model using virtual photons. So yeah, I mean, I didn't know that's what it was called, the G-2 of the electron, but That's cool. But like, I guess my point is though, bro, like quantum field theory is basically describing either. So like your answer is just that it's not needed, but this is what I don't get. Like it kind of is needed, right? Like what about vacuum energy, 0 point energy, wireless power induction in a vacuum, impedance of free space? Like, how is it not needed? Like I feel like it is needed. I guess I would hope to somehow encourage people as smart as you to at least be open to, like when you're doing your tests or looking into these things, just even simultaneously, like like kind of, I don't know the word, right, but putting both of the ideas beside each other and viewing them through the different lenses. Because every time that I've heard of someone doing that, that actually is like an expert, they tell me that like what they observe consistently fits within like an etheric framework better.
Well, I've
I
never
think
heard of that. I've never heard of
we're
that before.
overdue.
I've never heard of this myself, but as an answer to this, I'm an experimentalist. I'm not a theorist. This is something that is I leave it to theorists, and there are theorists that are coming up with lots of theories of alternative models. We're currently physics, high energy physics, is desperate to find a deviation of the standard model from of data from the standard model, because we find that it's too good. It's incredibly too good, and we don't find any deviation. And some theorists are not satisfied completely with the standard model because there are some theoretical parts that are not completely satisfactory, which are very not easy to explain. But and I'm not a theorist, so I'm not the best person to do that. But there are some open questions in the standard model. So people are looking for new physics desperately, and we're not finding any deviation, any experimental deviation. If you look at the program of searches at experiments such as the LHC, they're all called that. There's a whole section of physics programs that are called exotic or searches, meaning trying to test so-called exotic models that are not completely. Of course, they need to have the standard model as a limiting version, but they are extensions, possible extensions that are being explored of the standard model. So we continuously checking what these exotic models would predict and checking with experiments and see. And so far, we found nothing. We've
Well,
trying
just to
to.
clarify, you're talking about quantum field theory, though, right? Like,
Yeah.
special relativity was at odds with standard physics for many reasons, right? Because special relativity treats space-time as like this smooth, deterministic, and like local coordinate system, while quantum is like probabilistic and non-local. And you kind of like there were multiple issues with it, like locality and entanglement and whatever, and the wave function collapse and causality and all these things. So basically just deterministic versus probabilistic, and QFT was introduced to specifically to reconcile
Yeah,
special relativity and quantum.
yeah,
So then
and it does
so
at a
we're
level
throwing
that
out
is.
everything except for QFT, just to clarify for right, like when you're saying that it works incredibly well, specifically
Yes, it's
QFT.
QFT. Yes, it does. And standard model of particle physics, that's what I'm talking about, was produced and perfected in the 60s, when the for instance when the Higgs model was created and so on. And we have been testing it and trying to find extensions of it for decades, and we haven't found any. We have been looking for supersymmetric extension of the standard model. One of my professors was one of the fathers of supersymmetry. He was absolutely convinced that we would have found it at LEP, that we would have found it at LHC. We haven't found it yet. So there are things that some theories are predicting, and we're not finding it. But there are extensions. People are looking for, again, desperately looking for signals of new physics, so called, and we're not finding them. We've not found them yet.
Well, it's
there are
because you
some.
guys moved over towards more of an etheric framework, right? Like, so you fixed all of the
No,
discrepancies.
you think that if there was something like that, like what you're saying, that was viable, that was actually making viable
That's what
predictions,
QFT
people
is.
were not.
That's what I'm trying to say.
Well,
That's what QFT is. QFT was moving more towards an etheric framework where all of a sudden these particles weren't these little corporeal entities. They were ripples inside of fields that were permeating all of space, acting as a background. And all of the effects were localized excitations within those fields arising from that all-encompassing background that permeates all of space, which is much more etheric, which is why you could fix the problems that special relativity had. And then of course
yeah,
you then had the mathematical necessity of like antimatter, right? When you introduce QFT.
well, actually, was antimatter was before QFT, but okay, but it was introduced in the 30s, and QFT was actually developed in the late late
No, yeah, but
40s.
my understanding is that it was produced theoretically and all that, but like if you apply QFT, antimatter mathematically has to exist.
Yes.
But like yeah, anyway, so but do you see what I'm saying though? That like QFT is more etheric than the standard model was prior to the shift?
Yeah, but it's etheric, but it's completely consistent with special relativity. And the point of some people, some flat earthers, and science deniers, as I call them, to go back to ether, is that they want to have people like Alan Space Audit, that they want to the reason that they like ether is that because that would imply that the Earth is stationary and that the Earth is flat with the dome. So that's
No, no,
the
no. That
reason
first of
for
all,
them
no, brother, no. That
for
wouldn't
them to
imply.
invoke ether.
That's not even true. That wouldn't imply
I
anything to
think
do with
so.
shape or a dome, right? It would mean the Earth's not moving, but that would just be a necessary implication. The reason ether is preferable is it's the only model that works. Like we use it all the time. Like we use it in the
Ether the
lab
way
frame
was
all the time.
Ether the way it was used in before relativity was something different than what the ether, quote unquote, in QFT like fields, because fields in quantum field theory are formulated in a way that's relativistically covariant, and they are completely compatible with special relativity. There's no such thing as a preferred field frame. You
What?
have you have a everything that's described in a covariant way. So it's
Yeah,
perfectly
you
compatible
describe
with
it that
special.
way. That's cool. That's cool. But like what I'm saying is the only distinction at this point between an ether and QFT is this idea that all there is in the background are the fields. What do the fields exist within? What are the fields? The fields are waving. Well, what the antecedent to waving is a medium, right? And like you can dismiss this as philosophical, but that's the only reason you have special relativity is because someone named Einstein obsessively philosophized and figured out a different model, right? Without philosophy, you don't get a framework to do any of the experiments. But like there's really no difference at this point except a philosophically bankrupt difference, which is fields are not just math. So when I ask like what is a field, we're treating it as like an actual thing. The charged particles have actual resistance within the electromagnetic field. They're actual physical things. They're not just math. So when we define what a field is, we can't just say, oh well, it's any point in space and time. No, it's not just math. It's an actual thing, right? And what does it exist within? Where does all this background energy come from? That's all I'm saying. Like all I'm saying is if the reason that we say ether's preferable is just because it's the one that makes the most sense of all the tests. And we don't have to say, well, general relativity is a separate thing, throw it out. It's like, well, no, it would still exist where mass is. You can't really pick and choose. So ether allows you to not have to pick and choose. And it gives you an absolute reference frame to measure against. It gives you actual physical substantive qualities to have all the phenomena arise from. It gives you the primary substance you need for all of this phenomena. When we start to see this stuff pop in and out of existence, quote unquote, well, it's actually just the excitation of the background. So that's the reason. The implications of that when you now look at all the tests and experiments is that the Earth's not moving. That's true. It doesn't have anything to do with the shape of the Earth, though. But you know, I don't think that we just talk about the ether because we want to prove the Earth is flat. That's definitely not why I talk about it, right? Like I think it's one of the biggest things ever. It has major implications. I think it's held mankind back for a long time. You know, we made all kinds of progress whenever we thought there was an ether. That's how we created the electrical field, the electrical grid that we have to this day. That's how we created Maxwell's equations. That's how we created the Lorentz factor that you still use. All of that comes from an etheric assumption. All of it. You know, so like Maxwell's equations can't even be like utilized without an ether. So I don't know. I mean, we can just disagree on this maybe, but that's kind of the
Yeah, we
point.
definitely do. We definitely do because I've been using Maxwell's equations all the time without ether. But okay, I need to go now, really, because I'm really late. Sorry.
All right, brother. The point is you can't have Maxwell's equations without it. All right, man. I'll try. I do think that that guy is a very good resource, though, because he truly, wholeheartedly believes what he's saying, and he's just experimental, and he's just gonna tell you what's going on because he's excited to tell you,
Mm-hmm.
and it's cool because he's like, yeah, I mean, like there's a right hand, there should be a left hand based on the symmetry, but there's not. You know, he'll just straight up tell you, which is pretty cool.
Yes.
Yeah. Well, yeah. I mean, he jumped into the neutrino thing, but like, dude, they do like this GPS synchronization thing, and they use atomic clocks, and so they say, okay, I'm gonna shoot this neutrino beam, which really it's just like again, it's like high frequency electromagnetic waves that they use magnets to. That's what the same thing. All the particle accelerators are always using magnets, and they just
That's what they're
condense all the
calling
energy.
neutrino. Okay.
Yeah,
Thank you.
they condense all the
Wow.
energy into this small little dense beam, and then they just push a button basically, and it pulses out the electromagnetic waves. And like, okay, electromagnetic waves, speed of light. So, you know, if it's 3,000 miles away, then it's going to get there in however many microseconds because it's going the speed of light. So then the thing that receives it, they time it precisely from when it was sent, and then they open it up, right? This is the part that they open it up for just a couple microseconds, and then whatever they receive they just assume comes from what they shot. What they won't tell you is all the time they don't get anything. They don't get stuff all the
Right?
time, bro.
I
Yeah,
know.
they don't get the flashes. Basically, it's like a little flash. That's all they're seeing is a flash, and they're claiming it's a neutrino because it couldn't be a muon because the magnetic field they're using would deflect the muon because it's charged, like which is what he just explained, right? So they're just assuming that when they get the flash, it has to be a neutrino, and it has to be a neutrino that's sent from there because it was closed any other time. But if they receive flashes any other times, they'll claim, oh, this is just Right. Oh, this just came from space or whatever. So it's literally a Texas sharpshooter fallacy. It's just cherry picking the data, right? It's like if we don't get the flashes, whatever. And when we do get the flashes, we assume that's what it's for. And when we get the flashes outside of that window, we just throw them out. So we throw out 99.99999% of what we get. And then we just assume. So basically, if we get a flash outside of that timing window, oh, that's just background noise. Oh, it's just a cosmic ray. It's some type of mistake. If we get it right
Convenient.
during that, oh, look, it's proof of a neutrino that we shot to
The devil's in the
ourselves.
details. Yeah, the devil's in the details, Austin. And I'm glad you were able to walk through it with us for everybody who was listening here in the chat and out on YouTube land now or in the future. So, yeah. And it's interesting because you often hear them say that, oh, I'm just the experimental guy. You have to speak to the theorist. And then the theorist will say, oh, I'm just a theorist. You have to speak to the guy who's actually doing the practical science. So it's just this handing back and forth. And
Yeah, I like the experiment guys way more because, like, while I think that quantum is flooded with all kinds of like philosophically bankrupt reification fallacies and all this, the cult of bombarding particles, and the conflation of math and science. Like, you just saw what he did, right? That's all he does is conflate math and science. But like,
he's
um,
not alone.
it is
Yeah.
like one of the most experimentally valid fields in the world, meaning like quantum mechanics isn't all fake. It's like highly precise prediction, test, direct experimentation, physical manipulation. Um, like it's real. There is real science in quantum. So I'm saying, so if someone's like on the experimental side of that spectrum,
Yeah.
like that's pretty cool, right? Because they're
Yeah.
actually figuring out like cutting edge things. What they don't realize though, they're in God territory. in my opinion. They're literally trying to figure out exactly how the fundamental nature of reality comes from the background, the non-visible, like, foundation of existence. So they're like venturing into God territory. Like,
It's
meaning they're never
interesting
going
you
to
see that.
understand.
Absolutely. Sorry, I didn't mean to interrupt. It's just I heard that quote the other day from, I think it was maybe a Christian scientist who was quoted as saying, while doing experiments, we are trying to understand the mind of God. So I just heard that the other day, and it kind of reminds me of that. Thank you.
Yeah,
A lot of Christian
it's
scientists. I
pretty.
did want to ask him if he was a believer, but we never had that chance. Sorry.
I would doubt it, but I doubt it.
Oh, I was hoping that he would be. Then he could inspire maybe the people who don't right now. But yeah, maybe I'll ask in the future.
Thing about so most of the quantum physicists I talk to, right? Like, they don't like connect any of the observations to a need for a creator because that field is entered. There's probably exceptions or whatever, but like that field is entered with a false premise that like everything can be explained
Yeah.
in a reductionist, materialistic way. So the think about like the conundrum he's in. They're trying to explain immaterial things, like material sources, within a materialistic framework. Which is why when you ask them what a field is, they can't tell you what it is. They just
Hmm.
define it as math.
And when
It's
they
like
do that, I think they almost they're their own worst enemy because it's not a holistic approach that way. Imagine you have an entire encyclopedia at your disposal, but you go A through Y, but everyone that maybe excludes Z. You know, they're going to be lacking perhaps critical information to consider.
Yeah, I don't know.
So
Now I know though. Ever talking to him in the future, the like use case of it, there's really going to be no benefit of me trying to hit him with like this meta point of the ether is better.
yeah,
Yeah, we
it
should just
triggered.
talk to
I
him
heard
about
that.
the specifics of.
Did you hear that? It seemed to trigger something about the flat Earth
Yeah, yeah. Because
and the
he brought
dome and
up
all that.
Allen. He brought up Allen. Yeah,
Yeah.
so I'm guessing he has a history of going back and forth with Allen.
I do have an interesting side by side comparison here. I'd like to get your thoughts. I'm just going to drop it in the live stream here. And I've been sharing this with a lot of the globe believers or globe pushers. So it's just potentially when the United States found potentially the firmament 1962, the first time successful detonation in the atmosphere plane. And it looks a lot different from potentially detonation in free space. There's the video. But this was before the moon landings. I think that in the picture on the left, it's Operation Fishbowl, and that particular detonation was Starfish Prime, I think. But yeah, I'm sure you've seen the video by now.
Of the high altitude explosions, yeah.
Yeah, 1962. Yeah. And thank you. But yeah, I think there is
Yeah,
evidence
I
of the
don't know. It's very
firmament.
interesting. Yeah, the whole thing
Yeah.
is interesting. I just saw a guy just was on Joe Rogan like yesterday. He brought this up, and they claim that so there's one of the videos of the test like where it silhouettes on the sun, the explosion silhouettes on the sun,
Oh,
and as it happens, there's like this little thing that looks like it flies out of it downward, and he's claiming that they think it's a UFO or something. But the video is crazy. Like something like
interesting.
flies out of the explosion. Yeah.
Wow.
Yeah, so I don't think we have any idea what they were really doing. It's probably put something pretty crazy. I don't know. Like if they shot a
Yeah.
high altitude explosion and then all of a sudden some like little light shoots out of it down towards Earth, like what is that? I don't know. Because maybe they were opening up like, little places for things to pop through or something.
Yeah.
Yeah.
It's really interesting. And I think this is why, specifically, we don't have an uncut video from Earth, the surface, showing the straight horizon turn into a circle, despite 60 plus years and almost 2 trillion from NASA alone. Not even one video. That's especially since they had spent almost 100 billion on Artemis 1 and 2. So
Yeah,
not
what's
even
up
an
with that? Every time they shoot a rocket, it just cuts.
yeah.
Why?
And the
It
sad
cuts
thing
to
is,
like
I
a
don't think I've met a
cartoon.
globe. Yeah, and unfortunately, I don't think I've met a glober that is a little bit suspicious of that. Unless someone's in the voice channel right now who wants to step up and say, I believe the globe, but I kind of find that suspicious.
They must have like some comforting excuse that they all just cling to, right? So like, what do they say that I don't know. What can they say? That as they go
Oh no,
through the atmosphere, it's hard to keep showing the video. Like, I don't know.
oh, it's kind of sad. And actually, I think I have a way to show their bias. Maybe someone's listening, prove me wrong. So I just created a kind of like a comparison here. So it's what a globe believer believes potentially, and what a flat earther believes. So I've spoken to globers. Generally, they'll agree that NASA lies. Oh, sorry, the NSA lies, the CIA lies to the public, of course, right? For whatever reason, FBI will lie, but just the one agency that supports their position doesn't lie. Now, does that reveal their bias? I think so.
Yeah, that's pretty funny. These memes are good.
Thank you. No offense, but come on, guys. Is there a globe believer? I mean, the sad thing is, we have a globe believer in Bart Sibrel who's done more research related to the moon landing than probably all the globe believers here in this voice chat right now, and does not believe in the moon landing. And he doesn't even think the Earth is flat. So we have like a hostile witness who's done more research than a lot of the globers here. He's just trying to tell other people of this world that the United States did not land on the moon during Nixon. But there's so much attachment, right, to the globe, to the moon landing, I guess, for whatever reason. It's like a unicorn, a globe believer that does not believe the moon landing. But they're out there. There's a few. Probably none in the chat right now.